our discussion of the control flow structures that we have available in the Go language by talking about looping. Now in the last video, we talked about the two ways that we have to introduce branching logic into our application, if statements and switch statements. Well, when we talk about looping in Go, things are actually going to be a little bit simpler because we only have one type of statement that we're going to have to learn. And that statement is the for statement. Now we're basically going to break this conversation down into three different parts. We're going to talk about simple loops, we're going to talk about how we can exit a loop early, and then we're going to talk about how we can loop through collections. Okay, so let's go ahead and get started by learning how to do some simple loops in Go. So in order to start our discussion about looping in Go, I want to start with this, perhaps the most basic for loop that we can create. So we're going to start with the for keyword, as you might expect, and then we're going to follow the for keyword with three statements. The first statement is going to be an initializer. Now this is the same as an initializer in if statements and switch statements, so we can add any kind of statement that we want here, and normally we're going to use that in order to set up a counter when we're using a for loop like this. The next statement that we have here is going to be some kind of a statement that generates a Boolean result, and that's going to be used by the for loop to determine if it's done looping or not. And then the last statement is going to be the incrementer, and normally we're going to use that in a situation like this to increment a counter variable. So if we run this, we see that we get the numbers 0 through 4 printed out. We could also increment I by 2, and there you see that we only get 3 iterations of the loop because I has the value 0, then it has the value 2, and then it has the value 4. When it comes through the next time it has the value 6, well 6 is not less than 5, therefore the comparison operation results to false, and we exit out of the loop. So this is certainly possible to do, and you will occasionally see this, but the most standard way that you see these loops created is like this, using an increment statement. Now if you're coming from another language, you might be expecting to be able to do something like this. So maybe we want 2 variables to increment in our for loop, and so we're going to initialize j there, and then we're going to increment j with each loop. So if we go ahead and try and run this, we see that that's actually not allowed, because we have no comma operator in the Go language. So you can't separate two statements like this using the comma. So this is an error and this is an error. So if we want to do that though, we can use Go's ability to initialize multiple values at the same time by adding a comma here, getting rid of this part here, adding the comma there. And then we can't treat these as individual statements because you can only have one statement here, and in Go the increment operation is a statement, it's not an expression, so we need to figure out a way to do both of these at one time. So we will simply come in and set I and j equal to I plus 1 and j plus 1, and go ahead and run that, and now we have I printing out. If we add j here, we see that j prints out as well. We can actually increment j by 2 here, and we see that I and j are incrementing independently, and we have no problems here. Now just to come back and revisit that increment comment that I made earlier, you might be tempted to do something like this if you just want to increment them by 1. If we run that, we're actually going to get an error, because again, in Go, unlike a lot of languages, the increment operation is not an expression, so we can't use it as part of a statement, it is a statement on its own. So when you're just incrementing one variable, you can certainly do this because I++ is a statement, but we can't use that in combination with anything else. We can't use it as an expression. Something else that's interesting, let me go back to our initial example here so we can play around with this a little bit. So at first blush, if you're just coming to programming, this I variable might seem like it's something special because it's used up in the for loop, and the fact is it's a variable just like anything else. So we can do whatever we want with it. As a matter of fact, just to show you that, let me drop in this cool little bit of code. As you can see, what we're going to do here is we're going to take the modulus of I and 2, and we're going to see if that's 0. So basically we're checking to see if I is an even number or an odd number. If I is an odd number, then we're going to divide it by 2. If I is an even number, then we're going to multiply it by 2 and add 1 to it. It's just a couple things to play around with the incrementer. So let's run this and see if this actually goes to completion. And in fact it does, and you see that the I variable is going all over the place. So we start with 0, 0 is odd, so it divides that by 2, which stays 0. The next iteration, I is going to be 1 because we're incrementing by 1, so it's actually going to be multiplied by 2 and 1 added to it. So we print the 1 here, but then by the time we're done here, 2 times 1 plus 1 is 3, and so I is 3, that gets incremented to 4, so we're printing 4 out here. 4 is even, so we divide that by 2. 2 gets incremented again, so we print out the value 3. 3 is odd, so 3 times 2 is 6 plus 1 is 7. 7 is greater than 5, and so we leave the comparison operation. So we can do whatever we want with the counter. Now, just because you can play with the counter doesn't mean it's a good idea. As a matter of fact, normally it's very bad practice to manipulate the counter within the for loop. So maybe the best reason to show you that you can do this is to make sure that you avoid doing this, because there can be times when you're inadvertently changing the counter variable within a loop, and your loops might start to act really strange like we're seeing in this example here. Okay, so let's go ahead and restore our original example, make sure that that's running again, and it is. We're printing out the values 0 through 4 again. Now the next thing that I want to show you is that we don't actually need all 3 statements here. So one thing that we could do, let's just say that I is initialized somewhere else in our application, so we don't need I to be set up here, and we can run with this first statement being empty. Now you can't leave this first semicolon out, because if you leave that out, then everything's in the wrong place, and it thinks that this is going to be the initializer, and this is going to be the comparison operator. So if we try and run this way, we're going to get an error. But if we leave the semicolon in, then Go recognizes that we simply don't have an initializer in this for loop, and it executes everything the way that we expect it to. And of course that variable I is taken in just like we would expect. Now the difference between this format and the previous one is in this, I is scoped to the main function, but when we had this syntax here, I is scoped to the for loop. So if I tried to print the value of I out here, we're not going to get a valid value because I is not defined. But in this other form, when we're putting I out here, then I is scoped to the main function, and we are actually going to get the final value of I printed out, which is the value 5, because 5 is the first value that fails this test. So this is actually coming from this statement right here. Okay, the next thing that we can do, let me go ahead and wipe this out. We also don't need the incrementer value, so we can eliminate that. Now if I run this right now, we're actually going to get an error, because what this is going to do is it's going to generate an infinite loop, and in the Go playground, they don't let us do infinite loops, and so after it runs for a little bit of time, it's going to shut the process down on us. If we were actually running this in a local environment, all you'd see is the value 0 printed out over and over and over and over again, until eventually you got bored and shut the application down. Now we can, of course, since I is a variable just like any other, we can put the incrementer in here, and everything works just fine. So, once again, we have to remember to put the semicolon here. If we remove the semicolon, then Go doesn't know what the heck we're asking it to do, because this is invalid syntax. So if you have the first semicolon, you need the second semicolon. Now, this case does happen actually quite a bit, where we need a for loop and just a comparison operation. And this is how Go does do while loops. So in a lot of languages, you have 2 more keywords. You've got the do keyword and the while keyword. And normally those work with simply a logical test, and then you have some other increment operation. So you either have an incrementer inside of the loop, or you're pulling the next value off the stack and comparing that on each iteration, or something like that. Well, Go has the same problems to solve, but it didn't make sense for the designers of the language to introduce a new keyword just for what is basically a special case of a for loop. So what they allow us to do is we, of course, can use this double semicolon syntax here, but you can also leave them both off. So if I run this way, we see that this works, and this is going to work exactly the same way as if we have both of these semicolons here. So this is a little bit of syntactic sugar. It's exactly the same construct. It's just you don't need to have the additional semicolons, and it reads a little bit cleaner. So in this case, our for loop is just doing a comparison operation. Go is going to assume that we're taking care of where those variables for the comparison are coming from somewhere else. Now the third form of a for loop that we have available when we're working with counters like this is the infinite for loop. Because we also have a situation with do while loops in other languages where we need the application to run through the loop an undetermined number of times. And by undetermined means we don't actually know when to stop by an obvious logical test. We need some complex logic within the loop in order to determine when to leave. So in Go, the way that we do that is we simply leave off the logical test, and we run like this. So if I run this again, as you might expect, the playground's going to crash out on us because there's no way for the program to exit, and so it's just going to run forever. So we need some way to tell our infinite loop when it's done processing and when to leave. And the way we're going to do that is using the break keyword. Now normally the way that you do this is you'll put some kind of logical test inside of the loop. So we can say if I equals 5, then we're going to use that break keyword. And we saw the break keyword the first time when we were talking about switch statements. Well, the break keyword is actually more commonly used inside of for loops, especially this kind of infinite for loop here. So what we're doing here is if I is equal to 5, so we're going to print out the values 0 through 4 then when I equals 5, we're going to break out. So if we go ahead and run this, we get exactly the same values that we had before. Now when we do this, we actually leave the entire for loop. So execution of the loop stops, and we're done processing. Now another thing that we can do is use what's called a continue statement. So let me drop in an example that shows you that. So in this case, we're looping from 0 to 9 because we're going to keep incrementing as long as I is less than 10. And then we're checking to see if the value is even. If it is even, then we're going to use this continue statement here. And what this does is it basically says exit this iteration of the loop and start back over. So what's going to happen when we have 0, 0 modulus 2 is 0. So we're going to continue, which means we're not going to hit this print statement. When we have 1, 1 modulus 2 is 1, so we're not going to hit this continue, and we're going to print out 1, and then 2 is going to hit the continue, and 3 is not. So what we should see is we'll only print the odd numbers out. So if we run this, we see that that is in fact what happens. So continue statements aren't used very often, but they can be very, very useful if you're looping through a large set of numbers, and you need to determine within the loop whether you want to process a record or not. Now, to show you the next thing, I'm actually going to do this. This is actually going to print out a nested loop. So what we're doing here is a pretty simple example. We're starting with the variable I, initializing it to 1, and we're going to run as long as I is less than or equal to 3, and then we're doing the same thing with j on the inside. So basically I is going to be 1, then it's going to loop through j from 1 to 3, then I is going to be 2, it's going to loop through j from 1 to 3 again, and then inside this inner loop we're just multiplying the two numbers together. So if we run this, we see that we get all of the permutations of I times j, where I and j go from the values 1 to 3. So we get all of these values printed out, and everything works the way that we expect. Now what happens if we want to leave the loop as soon as we get the first value that's greater than 3? So what we want to do is something like this. So we're going to multiply I times j, we're going to repeat our logic here, and we're going to see if that's greater than or equal to 3. If it is, then we're going to break out of the loop. Now if I run this, we don't exactly get the expected result. And the reason for that is as soon as I times j is greater than 3, it breaks out of the loop. But the loop that it's going to break out of is the closest loop that it can find. So it's actually breaking out of this loop here, and this loop just restarts because there's nothing to tell it to stop. So you might ask the question, well, how do we break out of the outer loop? Do we have to have more logic here and check to see if I times j is greater than 3 again and then break out? Well, the answer is of course no. We do have a concept called a label that we can add. So a label is put together something like this. We're going to start with a word and follow it with a colon, and we're going to left justify that in our code blocks. So once I have a label defined, I can actually add the label after the break keyword, and it basically describes where we want to break out to. So since this label is just before this for loop, we're going to break out of the outer for loop. So if I run now, I get to the value 3. 3 is greater than or equal to 3, and so I break out of both the inner and the outer loop. The last thing that I want to talk about in this video is how we can work with collections with for loops. So we've seen this before. We have a slice of integers. In this case, we're containing the values 1, 2, and 3. And we've seen how we can work with this as a slice. So we can print this out. If we run this, we get no big surprise. We get the slice printed out with the values 1, 2, 3. But what happens if I want to work with each individual value? Well, we've seen how we can do this. We can pull out one value from the slice, and we get the value 2. But how do I work with an arbitrarily sized slice? So I don't know how big this slice is going to be at runtime. I want to be able to loop through all of the items within the slice. So the way that I'm going to loop through a collection is using a special form of the for loop called a for range loop. So I'm going to start that with the for keyword, as you might expect. And then what I'm going to get is both the key and the value for the current item in the collection. So I'm going to have two variables that I can set there. And then I'm going to set that equal to this special range keyword and then provide the collection that I'm going to range over. So what this is going to do is it's going to look at the collection here, and it's going to take each value one at a time, give us the key and the value, and then we're going to be able to work with those values independently. So inside of this, let's go ahead and just print out the value of the key and the value and run that. And you see that we get the indexes for the items in the slice, and we get their values. So the indexes are coming first, those are the keys, and then the values are the actual values in the slice. And this is the only syntax you have to remember when using the range keyword. You're always going to get this key comma value result coming out. So this syntax is going to work for slices and for arrays. So if we make this an array by just adding a size here, we see that we get the exact same output. We can loop over maps. So if I pull back the state populations map that we used for a couple of videos now, and loop over that, once again pulling out the key and the value, and ranging over the map this time. Then if I print the key and the value, I'm going to be able to split that out, and I get the state and their population printed out separately. And I can even use a string as a source for a for range loop, because what we're going to be able to do here is pull each letter out of this string as a character, and look at that. And we see that we do get each position, and now we get this numeric value, which if you've been paying attention over the last few videos, you're going to remember that this is actually the Unicode representation for that digit. So we can cast it back to a string by just using a simple conversion operation, and we see that we get each letter printed back out as we would expect. The other type of data that we can range over in Go is what's called a channel. Now, channels are used for concurrent programming in Go, and that's a topic for a future video. So I'm going to leave that topic right now, I promise. When we talk about parallelism and concurrency in Go, I'll revisit the for loop and show you how you can use for loops with channels, because there are some special behaviors that you have to be aware of when you're ranging over channels. Now, if I come back to this example and print this out, you see that we have access to both the key and the value every time. Now, this isn't always true. You don't always need access to the value, and this can lead to some problems, because if I only want to print the keys out and run this is actually an error, because in Go, you have to use every variable that's declared. So we got this situation where we've got this variable v, but we're not using it, and so that's going to cause us a problem with our application. Now, in Go, what you can do, if you only want to get the keys out, you can actually skip the comma value, and when you run that, it's going to ignore the value. But what happens if you get into a situation where you only want to print the value out? So if I restore this and I only want to print the value, of course I get the same error, but I can't just say this because Go is going to assign the keys to that. So what do? Well, in this situation, when you only want the values, then you can use that underscore operator, that write-only variable that we've seen a couple of times. And basically that's going to give a hint to the compiler that we don't actually care about the key, but we need this in this first position in order to get at the value. So when we run this, we do see that we get those populations printed out. Okay, so that covers what I want to talk about with for statements in Go. Let's go into a summary and review what we've talked about. In this video, we talked about the second major control flow construct that we have in the Go language, the looping construct. And we talked about how we're going to use the for statement for all of the loops that we need to do in Go. So we don't have to remember a do keyword and a while keyword and a for keyword. When we use the for keyword, that's going to allow us to loop over every collection that we have. We started by talking about simple loops and how there are three basic forms for the simple loop. We've got this first syntax, which is the most basic. That's the initializer test incrementer syntax. And we're going to use that initializer to set us up in our loop, normally by initializing a counter variable. Then we're going to follow that with our test. Our test is normally going to look at the incrementer to see if it's at a certain value that's out of range for our for loop. And then we've got an incrementer, and that incrementer's job is to move the incrementer along at every iteration of the loop in order to move to the next case that we want to loop through. Now, we also learned in this first syntax, we actually can leave the first and last statements on that out, but if we're going to use any of this syntax, we have to leave the semicolons in place. So leaving a semicolon out confuses the compiler. It starts to assign things to the wrong places, and so you're going to get an error in your application. So if you need an initializer or an incrementer, then you're going to have to use this full syntax. Now, the second syntax eliminates the need for the initializer and the incrementer, and it assumes that the test conditions are being managed somewhere else. So in this construct, you only have the for test, and as soon as that test is false, you're going to exit the loop. The last construct that we have is the for loop on its own, and that will run indefinitely until somewhere within your for loop, the break statement is called. That leads us to how we can exit early from a for loop, and we have three concepts that we talked about with that. We've got the break keyword that will break out of the immediate loop that's executing and continue the application execution after that loop. The continue statement is similar to the break statement, except for it doesn't break out of the loop, it just breaks out of the current iteration, goes back to the incrementer, and continues execution of the for loop at the next increment. Now, we can also use labels in our application and combine those with break statements in order to break out of an inner loop, and that's typically how they're used in Go. So for example, if you have a nested loop where you're iterating over two collections and you need to break out of the outer loop, then you need to set up a label and then follow the break keyword with the name of that label so that Go knows where to break out to. And finally, we talked about how to loop over collections and how the collections that we have available, there's quite a few. We've got arrays, slices, maps, strings, and channels that we can loop over, but they all have this similar syntax. We're going to use that for keyword, we're going to get a key and a value, and then we're going to set that equal to the range keyword followed by the collection that we're looping over. So the keys when working with arrays, slices, and strings are going to be the index within that collection, so you're going to have that zero-based index. With maps, we're going to get the key from that map. And the values are what you expect them to be. They're the value for that current index. Now, when we're talking about channels, it's going to follow very similar syntax, but channels have a little bit of a special interpretation for these, and we'll talk about those in a future module. I'd like to finish our discussion of control flow constructs that we have in Go by talking about defer, panic, and recovery. We'll start that discussion by talking about deferred functions, and how we can actually invoke a function, but delay its execution to some future point in time. Then we'll talk about how an application can panic. So in this conversation, we'll talk about how a Go application can enter a state where it can no longer continue to run, and how the Go runtime can trigger that, as well as how we can trigger that on our own. And then related to panicking, we'll talk about recovery. Now, when your application starts to panic, ideally you'd have some way to save the program so that it doesn't bail out completely. So we'll talk about if your application can be saved, how you can use the recover function in order to signal that to the rest of your application. Okay, so let's go ahead and get started. In a normal Go application, control flows from the top to the bottom of any function that we call. Now, of course, we can alter that a little bit by introducing branching logic so that we can skip some statements, and we can use looping that we talked about in the last video to repeat certain blocks of statements multiple times. But generally, a function is going to start at the first line and execute through until it gets to the last one. So if we run this program right here, we see that it's no big surprise that we print start, then we print middle, and then we print end. And what we can do if we want to defer the execution of one of these statements is precede it with the defer keyword. So if I put that in front of this print line here, then run that, you notice that middle is actually printed after end. So the way the defer keyword works in Go is that it actually executes any functions that are passed into it after the function finishes its final statement, but before it actually returns. So the way this main function is executing is it's calling line 8 and it's printing out start, then it recognizes that it has a deferred function to call, and then it prints out end, and then the main function exits. Now when Go recognizes that that function exits, it looks to see if there are any deferred functions to call, and since we have one, it then goes ahead and calls that. So deferring doesn't move it to the end of the main function, it actually moves it after the main function, but before the main function returns. Now if we put the defer keyword in front of all of these statements, then we'll actually see an interesting behavior, because the deferred functions are actually executed in what's called LIFO order, or last in, first out. So the last function that gets deferred is actually going to be the first one that gets called. And this makes sense because often we're going to use the deferred keyword to close out resources. And it makes sense that we close resources out in the opposite order that we open them, because one resource might actually be dependent upon another one. So if we run this like this, we actually see that we've reversed the order of printing this. So we're now printing end, middle, and start. And just to remind you, these aren't executing in the context of the main function. They're executing after the main function is done, but before it returns any results to the calling function. Now these are good theoretical examples, but in this situation, I felt it makes sense to get a little bit more practical example for you to look at. So for this, we're actually going to need to go into Visual Studio Code, because we're going to need to run a program that's going to make some resource requests through the HTTP package, and you can't do that in the Playground. So if we look at this program here, we're importing a couple of packages, then we're using the get function from the HTTP package in order to request the robots.txt file from google.com. Now this example you can actually find in Go's documentation. I basically stole this as an example for how you can use the deferred function. Now as you can see with this request, we're going to get a response and an optional error, and we're going to check to see if that error is nil, and if it's not, then we're going to log that out and exit our application. If it is not nil, then we got a good response. So then we're going to use the readAll function from the IOUtil package. What that'll do is that'll take in a stream, and that'll parse that out to a string of bytes for you to work with. So if we look at the robots variable here, we see that that is a string of bytes. And then we close the body of the response to let the web request know that we're done working with it, so it can free up those resources. Of course, the read operation can fail, so we're checking for that error. And then we're finally going to print out the value of the robots variable here. So if we run this application by invoking it with the go run command, we see in fact that we do get the robots printed out, and everything worked out just fine. So we got this entire response printed out to the console here. Now one thing that we're doing here that the defer keyword can help with is handling this body close. Now in this application, we only have one statement that's really being worked with between the request being made and the body being closed. However, in many applications, you might have quite a bit of logic that's involved that needs that body to be open and continue to work with it. Maybe you're reading the stream one character at a time, and you're doing some pattern matching or something like that. So you can actually end up with quite a few statements in here. So what can happen here is that you might make this request and open up this resource up here, and then it might be dozens of lines later that you actually get around to closing it. Well, that introduces the possibility that you forget to close it. Now, it's going to be hard to find that, and it's going to be hard to remember to close the resource, and so you're introducing the possibility of bugs coming into your application. So what we can do is add the defer keyword here, and then we can go ahead and move this up a line. So if we run this, then it looks like we're closing the resource and then we're trying to read it. But if we run the application, we see that it works just fine. Everything comes out the same way it did before. Now, if we leave the defer keyword off, then we do get an error because we closed the response body before we were done reading it. So what this allows you to do, and this is the most common use case that I've seen for using defer, is it allows you to associate the opening of a resource and the closing of the resource right next to each other. So you see this pattern a lot, where we're going to open a resource, we're going to check for an error, and then we're going to close the resource. Now you want to check for the error first, because if there's an error generated here, then you actually never got this resource, and so trying to close it will cause your application to fail. But as long as you know that you have the resource there, then it makes sense to do a deferred call to close it. Now, one thing I would warn you about is this is a pretty common pattern, and you're going to see this all the time, but if you're making a lot of requests and opening a lot of resources within a loop, then using the defer keyword to close it might not be your best choice. Because remember, the deferred statements don't execute until the function itself executes. So if you've got a loop that's going to loop over 1 million resources, you're going to have 1 million resources open before all of those get closed at the same time when the function finally executes. So if you're working with resources in a loop, then you might not actually want to use the defer keyword. You might want to explicitly close those resources when you're done with them. Or another option would be to delegate the processing of those resources out to another function and have that function close the resource. That way you're not keeping a bunch of resources open at one time and wasting memory. Now the next thing that I want to show you, we can do back in the playground. So I want to do that because I think that's the most accessible environment that we have, is this program here. So when I run this program here, what do you think is going to print out when I run this? Now there's two lines of thought that you might have. The first line of thought is, well, I'm defining A as the string start, and so I'm going to print start out, but you might also realize the defer statement is going to cause this statement to print after the main function is done, and before main is done, we've already changed the value to end. So you could make an argument that this is going to print start or end. Well, the fact is that we're going to get the value start printed out. And the reason for that is when you defer a function like this, it actually takes the arguments at the time the defer is called, not at the time the called function is executed. So even though the value of A is changed before we leave the main function, we are going to actually eagerly evaluate this variable, and so the value start is going to be put in here. We're not going to pay attention to this value as it changes. Now the next thing that I want to talk to you about in this video is what's called panicking. Now in Go, we don't have exceptions like a lot of applications have, because a lot of cases that are considered exceptional in a lot of languages are considered normal in a Go application. For example, if you try and open a file and that file doesn't exist, that's actually a pretty normal response. It is reasonable to assume that you might try and open a file that doesn't exist, and so we return error values, we don't throw exceptions because that's not considered exceptional in Go. However, there are some things that get a Go application into a situation where it cannot continue, and that is considered exceptional. But instead of using the word exception, which has a lot of connotations because of its use in other languages, we're going to use another word, and that word is going to be panic, and that's because our application can't continue to function, and so it's really starting to panic because it can't figure out what to do. So if we take this example here, I'm declaring two variables, A and B, and setting A equal to 1 and B equal to 0. Now, obviously, the answer of 1 divided by 0 is invalid. We can't do that in a Go application. So if I run this, we're actually going to see that the runtime itself will generate a panic for us. And the runtime error is printed out, integer divided by 0, and then we get a stack trace letting us know where that error occurred. Now, if you're going along and writing your own program, and you get to a situation where your program cannot continue to execute because of a certain state that gets thrown, then it makes sense for you to panic as well. So to do that, you're going to use the built-in panic function like we see here. So we're printing out start, then we're using the built-in panic function, passing in a string, and then we're going to print out end. Now what's going to happen when we run this is very similar behavior to when we had that divide by zero error a few seconds ago, but the error message that's printed out is actually going to be the string that we pass into the panic function. And then notice we get the same stack trace out. We do get start printed out, but of course we don't get the string end printed out. Now, a more practical example, now this will not run in the playground, but that's okay because it probably wouldn't fail in the playground anyway, is this one here. So this is a very simple web application where you're going to use the handle funcs. So we're registering a function listener that's going to listen on every URL in our application. And then this is a callback that gets called every time a URL comes in that matches this route. And all this is going to do is print out the string hello go. As a matter of fact, why don't I go ahead and do this over in Visual Studio Code? That way you can see what this program is going to do. So we'll go ahead and save this and we'll get it up and running. Now there's no errors. It went ahead and started okay. So if I come in and hit that URL, which is at localhost 8080, then you see that we get the string hello go printed out. There you go, an entire web development course in one video. So we've got a very basic web handler that's printing out the string hello go, and that's coming from this line right here where we're writing to this response writer. This response writer is basically giving us access to the response to this web request, and we're printing out the string hello go. Now, what's interesting here is this error handler right here. So the listen and serve function returns an optional error object. So when might that happen? Well, one situation that can happen all the time when you're firing up a web server is the port could be blocked. So if I open up another terminal here and go ahead and try and run this again, you see that we get our application panicking. And the reason for that is we're trying to access a TCP port that's already been blocked. And it's been blocked by the fact that we're running the application over here. So this is a situation that happens all the time. Now, the listen and serve function doesn't have an opinion on if that's a panicking situation or not, because it just tried to execute something and it's going to return an error value saying, well, that didn't work. It's reasonable to assume that listen and serve can fail. And so it's not going to panic, it's going to return an error. Now, we're the ones writing the web application, and we know that if that doesn't work, the entire application gets brought down and nothing happens. So in that situation, we decide that we're going to panic passing out that error that comes from the listen and serve method, letting whoever's trying to start this up know that something very bad just happened. So this is a common pattern that you're going to see in Go. Go is rarely going to set an opinion about whether an error is something that should be panicked over or not. All it's going to do is tell you, hey, this didn't work the way that you expected it to work. It's up to you as a developer to decide whether that's a problem or not. So in this case, we say, yeah, that is a problem. We failed to start our application, and so we do want to generate a panic. So what are we going to do in the situation that our application is panicking? And we can get ourselves to a situation where we can recover the application. So panics don't have to be fatal. They just are if we panic all the way up to the Go runtime, and the Go runtime realizes, well, it doesn't know what to do with a panicking application, and so it's going to kill it. So we come back to this application here and run. We see that once again we're getting this panic. But something I want to show you related to our deferred discussion is this modification here. So I've added this line, a deferred print statement that says this was deferred. So if we run this application, something interesting is going to happen. We get start printed out, that's not a big surprise, but then we get this was deferred printing out, and then the panic happens. And this is really important because panics happen after deferred statements are executed. So the order of execution is we're going to execute our main function, then we're going to execute any deferred statements, then we're going to handle any panics that occur, and then we're going to handle the return value. So there's actually quite a bit that happens in a function after it exits this closing curly brace here. So why is this important? Well, the first thing that's important is that deferred statements that are going to close resources are going to succeed even if your application panics. So if somewhere up the call stack you recover from the panic, you don't have to worry about these resources being left out there and left open. So any deferred calls to close resources are still going to work even if a function panics. But the other thing that's really important is if I change my deferred function here to something like this. Now this is a custom function and we're not going to talk about this for a couple of videos yet, but this is important in order to talk about this, so I need to jump this ahead in the queue a little bit. So what we're creating here is what's called an anonymous function, and an anonymous function is simply a function that doesn't have a name, so nothing else can call this. This is defined at one point and we can call it exactly one time. These parentheses here are making that function execute. And this is an important thing to know about the defer statement. The defer statement doesn't take a function itself, it actually takes a function call. So you want to invoke that function, otherwise things aren't going to work properly. Now inside of this custom function, notice that we're using this recover function here. So what the recover function is going to do is it will return nil if the application isn't panicking, but if it isn't nil, then it's going to return the error that actually is causing the application to panic. So in this logical test, we're checking to see if it's not nil. So if it's not nil, that means our application is panicking. And in this situation, we're simply going to log that error out. Now what happens in this situation is the execution still stops at the panic. And let me import this log package before we run this. And we see that the application still executes. So we got the string start printed out, then we printed out the error using the log package, but we didn't get this end function printed out. So it looks like our application is still dead, but recover does have some important impacts if we have a deeper call stack than what we're dealing with right here. So let me drop in this example in order to show you. So in this case, we got the main function that's going to be our application entry point, of course. And then we've got this other function called panicker. And all this thing does is it's going to print out a line that says it's about to panic, and then it's going to panic, and it's going to go ahead and recover from that panic using that deferred function that we saw just a moment ago. Then we're going to have this line here, done panicking. And then up in our main function, we're going to print start, we're going to call the panicker, and then we're going to print end. So let's see what happens when we run this. So as you see, we get the start line printed out like you would expect. We see the about to panic string print out. Then we panic, something bad happened. We go into our recover loop because we're not going to execute this because our application panicked, and so our panicker function is going to stop execution right there and execute any deferred functions. And inside of that deferred function we call recover. So in that recover, we're going to log out the fact that we have that error, and we're going to log that error message out that we see here. But then in the main function, execution continues. So in the event that you're recovering from a panic, the function that actually recovers still stops execution because it's in a state where it can no longer reliably continue to function, and so it makes sense for it to stop doing whatever it was trying to do. However, functions higher up the call stack, those functions that called the function that recovered from the panic, they are still presumably in a situation where they can continue because your recover function said that your application is in a state where it can continue to execute. Now this is a little bit limiting as well, because in order to determine what that error is, you actually have to call the recover function, which basically means that you're saying that you're going to deal with it. So what happens if you get that error and you realize that this isn't something that you can deal with? Well, in that case, what you're going to do is repanic the application. So all we need to do in order to do that is just rethrow the error, or you can come up with another error string, whatever makes sense for you. But in this case, inside of the handler, we're throwing a panic again. Then we actually see that we don't get that end statement printed out. Our main function panics because we rethrew that panic. So we get the full stack trace of when the panic actually happened, and we see that we're inside of func1. Func1 is actually this anonymous function right here. And we see that we do get that stack trace printed out, and we don't get the string end printed out. So if you're in a situation where you're trying to recover from a panic and you realize you can't handle it, you can feel free to rethrow that panic and defer the management of that panic higher up the call stack. Okay, so let's go into a summary and review what we've talked about in this video. In this video, we talked about the final two control flow concepts that we have to be aware of in Go programming. Now, one could argue that defers and panics aren't really control flow constructs because they're not the traditional branching or looping logic that we consider, but they definitely do alter the flow of execution of our program, and so I'm going to lump them together in this category. The first thing that we talked about was the use of the defer function in order to delay the execution of a statement until the end of a function. Now these are useful to group open and close functions together. So if your open function is going to open up a resource and you need to make sure that you close that, then you can defer the call to close that resource to make sure that you're freeing up the memory and not holding onto that resource any longer than you need to. The one thing I would warn you though is be careful in loops. If you're opening and closing a bunch of resources inside of a loop, then you probably want to explicitly handle that close without the deferred keyword, because when you're using the deferred keyword, all of those resources are going to stay open until the function finishes execution, and that can cause you some memory issues, especially if you're dealing with a very large number of resources. Now, if you've got multiple deferred statements inside of a function, then they run in LIFO order, or last in, first out. So the last deferred statement that you call is going to be the first one that actually executes. And again, this makes sense because if you're opening a bunch of resources and those resources are dependent upon one another, then you're going to close them in the reverse order that you open them, which is typically the right way to go. Arguments in a deferred call are evaluated at the time the defer is executed, not at the time the called function is executed. Now that's important to keep in mind because you could pass in variables into a deferred function call, and it can be a little bit confusing if you change the value of those variables further on and those aren't reflected in your deferred statement. So just keep in mind, when you call defer, the value of those variables are going to be captured at the time that defer is executed, not at the time the function actually executes. Now, something unplanned happens in our application, then we've got two ways that a Go application can go. It can return an error value, which is the normal case, or it can panic. Now, what you generally want to do is you want to return an error value because in Go programming, we typically don't consider a lot of things that go wrong in an application to be exceptional events or to be events that should cause the application to shut down, for example. A classic example of that is making an HTTP request and you make the request and you don't get a response from that server. Well, that's something that happens all the time. No response is a valid response. It just happens to be an error because you're looking for that resource and you got a 404 return back. So in that case, you're going to return an error value. You're not going to panic the application. Panics are used when an application gets into a state that it cannot recover from. For example, if you hand the runtime a divide by zero problem, there's no way for Go to figure out how to divide a number by zero, and so it has no way to manage that. And that's a situation where the application is going to panic. So just to summarize that, they occur when an application can't continue at all. Don't use them when a file can't be opened, unless it's a critical file. For example, if you're opening a template that's used in a web application to generate your view layer, then that might be something that's worth panicking over. But if you're trying to open up a log file and you can't get there, well, there's no reason to panic for that necessarily. You just need to return an error value and then inform somebody that the logs aren't available. Now, a situation where you might want to panic is unrecoverable events. So if you're starting up a web server and it can't get a hold of the TCP port that it's supposed to be listening on, then that's probably a situation where a panic makes sense. The function will stop executing immediately at the point of the panic, but deferred functions will still fire. If nothing handles that panic, then eventually the panic is going to go up the call stack, it's going to hit the Go runtime. The Go runtime has no built-in handling for panicking situations, and so the program will then exit. If you do have a panicking situation that you feel that you can recover from, then you can recover using the built-in recover function. Now that function is used to recover from panics. It's only useful inside of deferred functions, and the reason for that is because of the behavior of panic. Remember, when an application starts to panic, it no longer executes the rest of that function, but it will execute deferred functions. So the proper place to use the recover keyword is inside of a deferred function that's going to look for a panicking situation, and if the application is panicking, then it can go ahead and decide what to do with it. The current function will not attempt to continue, but if you do recover, then higher functions in the call stack will continue as if nothing went wrong. Now, if that's not the behavior that you want, if you call that recover function, you look at the error that's returned from the recover function and you can't handle it, remember that you can go ahead and rethrow that panic by calling the panic function again, and then the panic will continue to propagate up the call stack. I want to talk about pointers and how we can use them in the Go language. We'll start that discussion off by learning how to create pointers, and then we'll talk about something called dereferencing a pointer, which is basically using a pointer to get at some underlying data. Then we'll talk about the new function, and then we'll talk about a special type in Go called nil, and then we'll wrap up our discussion by talking about built-in types in Go that use internal pointers, and so their behavior is a little bit different than other types that you'll work with in your applications. Okay, so let's dive right in and learn how to create some pointers. To start our discussion, I want to start as simply as I can, and so I'm going to use this example here. As you can see, I'm declaring a variable a and assigning it the value 42, and then I'm going to go ahead and print that out. So it should be no big surprise that when I run this, the value 42 gets printed out. Now, if I extend this application a little bit, and I create a variable b and assign it to the value of a, and print both of those out, then again, it's no big surprise that 42 prints out 2 times. Now, since a and b are value types, when I put in this line here, what Go is going to do is it's actually going to copy whatever data is stored in a and assign it to b. So we're not actually pointing to the same memory, and we can prove that by changing the value of a to, for example, 27, and then printing out everything again. And if we run this, we see that the value of a changes to 27, but the value of b stays at 42. Now we can change this behavior a little bit by having b point to a using something called a pointer. Now in order to demonstrate that, I'm going to actually change our declaration syntax a little bit and go to more of a long form syntax. And the reason for that is to make things a little bit more clear about how the pointer notation works. So I hope you'll agree with me that this line 8 is exactly the same as the previous one that we had, it's just a little bit more verbose. Now if I want to change b into a pointer and use that same long form syntax, what I can do is declare the variable b, and then I'm going to declare it as a pointer to an integer. And the way I declare it as a pointer is by preceding the type that I'm pointing to with this asterisk here. So then if I want b to point to a, then I'm going to use a special operator called the address of operator that you see here. So what line 9 is now saying is that b is a pointer to an integer, and I want to point it to a. Now what is a pointer exactly? Well, let me remove these lines here and run this and see what we get as output. So as you see here, a is still holding the value 42 like we expect, but b is holding this strange data here. So what is that? Well, this is actually the numerical representation for the memory address that is holding the location of a. So at this location in memory, we actually have assigned the integer 42. So b isn't holding the value 42, it's holding the memory location that's holding a's data. And we can prove that by using the address of operator down here. And when we run this again, we should see, and in fact we do, see that the values are exactly the same. So the address of a in memory is this value here, and b is holding that exact value. And as a matter of fact, we can even go the other way, because while the address of operator is going to give us the address of a variable in memory, we can use a different operator in order to figure out what value is actually being stored at a memory location. And that's called the dereferencing operator. So if I go ahead and remove this, and then I'm going to put a dereferencing operator right here in front of this pointer. Now you notice we're using the same asterisk, but these have a little bit different meaning here. So up here on line 9, this asterisk before a type is declaring a pointer to data of that type. So this is a pointer to an integer. Now when I put the asterisk in front of a pointer, then that's going to dereference, which basically means it's going to ask the go runtime to drill through the pointer, find the memory location that that pointer is pointing to, and then pull the value back out. So if we run this, we see that we get the value 42 printed out both times once again. Now what's the point of all of this? Well, the point is, since b is pointing at the same value of a, now both of these variables are actually tied together. So if we change the value of a once again, and then print out their data, now we see that both a and dereferencing b both give the value of 27 because they're both actually pointing at the same underlying data. As a matter of fact, we can even dereference the pointer and use that to change the value. So if I use the dereferenced b and assign the value 42 to it, and then print this out again, then we see that once again, both values are changing. A and the value that b is pointing to are both changed because it's in fact the same data. Now if you come from a background in languages that allow you to work with pointers as variables, then you might be expecting to do something called pointer arithmetic. So if I drop this example in here, we're going to start to play around with something that's going to lead us to see how Go treats pointer arithmetic. So I'm going to start with the variable a, and that's going to hold an array of 3 values, 1, 2, and 3. And then I've declared b as a pointer to the first element in the array, to this value right here, and then c is pointing to this second element right here. Now if I use this print statement here, it's going to print the value of the array, and then this %p syntax is actually going to print the value of the pointer for b and c. So if we run this, we see that we do in fact get the array, and then we get these 2 memory locations printed out that b and c are holding. Now notice that c is holding a value that's 4 higher than b. And the reason for that is how Go lays out arrays in memory. Since this is an array of integers, and integers in this version of the runtime are 4 bytes long, each element of an array are 4 bytes apart. So this memory address ending with 124 is holding the first element in the array, and then 4 bytes later, we're going to hold the next element of the array. So you might be tempted to do something like this if you come from another language. If I take the address of C and subtract 4, then that actually should give me the address of B, and then I can dereference that, and both of these should be pointing to the head of the array. Well, if I run this, I in fact see that I get an error. And the reason for that is Go does not allow math like this to be done on pointers. Now once again, if you've come from C or C++, you're probably aware of the tremendous performance advantages that you can get if you're allowed to do pointer arithmetic, because you can jump around mapped memory very, very quickly and gain some pretty substantial benefits in the performance of certain applications. However, Whenever you get into pointer arithmetic, you are typically getting into some fairly complicated code, and since Go has as one of its core design concerns simplicity, the decision was made to leave pointer arithmetic out of the Go language. Now, if you absolutely need to have something like this in your application, then what I would suggest is you can come into the Go packages and come down here to the unsafe package, and this is going to give you operations that the Go runtime is not going to check for you. So if you really need to do pointer arithmetic and things like that, then the unsafe package, which has a very appropriate name, is available for you for those very advanced scenarios. Now, those scenarios are advanced enough that what I'm going to suggest is if you need to know it, you're going to learn it, but generally you're not going to need to know how this stuff works. Now, the next thing that I want to show you is how we can actually create pointer types. So we've seen this address of operator, and that's allowing us to instantiate a pointer to a certain variable. So if we look at the type of B, it's actually a pointer to an integer because we're pointing to one element in the array. But so far we've had to declare the underlying type first. Well, that's actually not necessary in Go because often you only want to work with the pointers and you don't really care where the underlying data is stored. You just need the ability to point to it wherever it's at. So in this example, we see how we can do that. Now, we've seen almost exactly the same syntax before, because when we were talking about structs, we had an example that looked something like this. So we were declaring a myStruct object, we were instantiating it using the object initialization syntax, and when we print everything out, we print the value 42 out. Now, if I make this ms variable a pointer to a myStruct, and then use the address of operator in this object initializer, then I actually get almost the same behavior, except for notice that when I print out the value of ms, I end up with this ampersand here, which is basically saying that ms is holding the address of an object that has a field with the value 42 in it. Now, the advantage of being able to do this is going to come to light in a future video, but for now, just be aware that you can do this. Now, this isn't the only way that we have available to us to initialize a variable to a pointer to an object. We can also use the built-in new function. Now, unfortunately, with the new function, we can't use the object initialization syntax. We're just going to be able to initialize an empty object. So if I go ahead and run this, we see that we do get an initialized object, but all of its fields are initialized to their 0 values. We can't initialize them using the object initialization syntax. Now, since I mentioned 0 values, it's important to understand the 0 value for a pointer, because as we talked about in a very early video, every variable that you declare in Go has an initialization value. So right here after line 8, ms is holding something. So the question is, what is that thing? So if I go ahead and copy this print statement up here, we'll be able to answer that question. So let me format this and run it. And then we see that we get the special value nil out. So a pointer that you don't initialize is actually going to be initialized for you, and it's going to hold this value nil. So this is very important to check in your applications, because if you're accepting pointers as arguments, it is best practice to see if that pointer is a nil pointer, because if it is, then you're going to have to handle that in a different way. So for example, if we try and drill through and get to this foo field, but ms is actually nil, then we're going to get a runtime exception and our program's going to crash on us. Now that actually leads us to an interesting point. How do we actually get at this underlying field and work with it? Well, the obvious way that we're going to need to do that is we're going to have to dereference the ms pointer in order to get at that struct, and then we can get at that field. So we're going to have to use something like this. Now you might be asking why the parens are there. Well, it turns out that the dereferencing operator actually has a lower precedence than the dot operator, so we need the parens in order to make sure that we're dereferencing the ms variable instead of dereferencing ms.foo. So now we can go ahead and set this to the value 42. Now in order to get at the value of foo to print it out, then we're going to have to repeat the same exercise. So I'm going to add some parens here. I'm going to wrap this ms variable, and then we'll print out the value of foo. So if I go ahead and run this, we in fact do set and get the value 42, which is the value of that field. Now I hope you'll agree with me at this point that this syntax is really ugly. Because if we use this syntax, every time we dereference a pointer, we're going to have to use a matched set of parens and have this dereference operator. Well, it turns out, because of the limitations that are put on pointers, the compiler is actually able to help us out a little bit. So in fact, we don't need this syntax at all. If we go ahead and remove this from the print statement as well, and run this, we actually get exactly the same behavior. Now again, if you're coming from a language which makes extensive use of pointers, this is probably freaking you out, because the pointer ms doesn't actually have a field foo on it. The pointer ms is pointing to a structure that has a field foo. So how is this working? Well, again, this is just syntactic sugar. This is just the compiler helping us out because it understands we're not actually trying to access the foo field on the pointer. We're implying that we want the underlying object. And so Go is going to go ahead and interpret that properly for us and dereference the pointer. So the compiler really sees this statement the same as this statement. They're exactly the same to the compiler. It's just one reads a little bit more cleanly. Now the last thing that I want to talk about today is how Go handles variables when they're assigned one to another. So let me go ahead and paste this example in here. As you can see on line 8, we're initializing an array. On line 9, we're initializing another variable and pointing it to the same array as A. Then I'm going to print out both A and B. And then I'm going to change index 1 of the A array to 42 and print them out again. Now we've already done this example in the past, and hopefully you remember that A is going to change, but B is not, because B is a copy of the array that we stored in A, and so they update independently of each other. However, if I remove this index and turn this into a slice, the behavior changes a little bit. If we run this, now we see that both A and B are changed together. So what happened there? Well, the slice is copied just like the array, but the effect of the copying is a little bit different. Because in the version with an array, the values of the array are actually considered intrinsic to the variable. So A is holding the values of the array, as well as the size of the array. And that size is held, that way we can do bounds checking. So for example, if we ask for index 3, which is beyond the bounds of this array, and run, we can do bounds checking in the Go language, and that's a very good thing. However, with slices, remember, a slice is actually a projection of an underlying array. And so the slice doesn't contain the data itself. The slice contains a pointer to the first element that the slice is pointing to on the underlying array. So what that means is that when we work with slices, the internal representation of a slice actually has a pointer to an array. So while line 9 is still copying the slice A into the slice B, part of the data that gets copied is a pointer, not the underlying data itself. What that basically means is when you're sharing slices in your application, you're actually always going to be pointing at that same underlying data. Now the other built-in type that has this behavior is a map. Because maps, once again, have a pointer to the underlying data. They don't actually contain the underlying data in themselves. So if I take this example where I'm initializing a map of strings to strings and assigning that to A, and then B is assigned to A, then I print them both out, then I change one of the values in A and print them out again. If I run this, we see that both maps start out the same, and then when I change the key foo in the map A, we actually change that in the map B as well. So what does that mean? Well, what it means is when you're working with slices and maps in a Go application, you have to be very, very careful to keep in mind at all times who's got access to that underlying data. Because passing slices and maps around in your application can get you into situations where data is changing in unexpected ways. However, if you're working with the other data types, specifically primitives, arrays, or structs, then this generally isn't going to happen to you because when you copy a struct, it's actually going to copy the entire structure unless you're using pointers. Okay, so that wraps up what I have to talk about with pointers. Let's head into a summary and review what we've talked about in this video. In this video, we talked about pointers and how to use them in the Go language. Now, we haven't seen a lot of practical application for pointers yet, but we need to understand what pointers are before we get into that. So over the next couple of videos, we'll get into why you would want to use pointers and the benefits of them, but for now, we're just trying to introduce the basic subject. So we started by learning how to create pointers, and we learned that if we prefix a type with an asterisk, that's actually going to declare that type to be a pointer to that underlying data type. So for example, we have this asterisk int, which is going to be a pointer to an integer. We also learned how we can create pointers using the address-off operator to get the address of an existing variable in memory. Then we learned about dereferencing pointers and how we can use that asterisk operator again, but this time in front of a pointer instead of in front of a type, and use that to drill through the pointer to get at the value that the pointer is pointing to. We also learned that when you're working with complex types, such as pointers to structs, those pointers are automatically going to be dereferenced for us, so our syntax doesn't get cluttered up by a whole bunch of dereference operations and parentheses. Then we moved on to learn how to create pointers to objects. And we learned that there's a couple of different ways. So the first thing that we could do is use that address of operator to get access to a pointer to an object that we've already created. So in this example, we've got an instance of a myStruct object called ms, And then we can use that address of operator to create a pointer p to that struct. But we can also do that directly. So if we precede an object initializer with that address of operator, then we can actually directly create a pointer, and we don't have to have an intermediate variable that's holding that value. We can also use the new keyword to initialize an object, but we can't initialize the fields at the same time. So the behavior is a little bit different because we're going to have to use the new keyword that's going to zero out all the fields in a struct, for example, and then we're going to have to come in later and initialize all the values. The last thing that we talked about was types with internal pointers. And we saw how, while they're treated exactly as any other variable type when we do an assignment, their behavior is a little bit different. So all assignment operations in Go are copy operations. So whenever you have a variable A and you create a variable B and set it equal to A, all of the data in A is going to be copied in order to create B. However, slices and maps contain internal pointers, and so even though they're copying pointers, and so they're pointing to the same underlying data. We're going to take a deep dive into functions and how you can use them in the Go language. Now, we've been talking about functions throughout this entire video series, but we've never really taken the time to focus on them because there's a lot of groundwork that we've had to go through building up to the point where we can understand what a function is and how we can use those in our applications. So in today's video, like all of our videos in this series, I'm going to break the discussion down into multiple parts. We'll start by talking about the basic syntax of a function. Then we'll talk about the parameters that you can pass into a function to influence how it works. Then we'll talk about the return values that you can get back out of a function. We'll talk about something called an anonymous function. We'll talk about how functions in the Go language are first-class citizens and can be passed around in your application like any other variable. And then we'll wrap up our discussion by talking about a special kind of function called a method. Okay, so let's get started by learning the basic syntax of a function. To start our discussion of functions, we don't have to go any farther than the basic application that the Go Playground gives us. So as soon as you come into the playground, you're presented with this very simple application, and right here we have our first function. Now the way that a Go application is structured is you always have to have an entry point in the application. And the entry point of a Go application is always in package main, and within that main package you have to have a function called main that takes no parameters and returns no values. So we can see that right here. And so when we run the application actually starts right here. And so we print out the string hello playground, and that's all that our application has to do. So every Go application starts this way, and we see here the most basic function that we can create in the Go language. So there are several major parts that we need to understand about a function. First of all, they start with the func keyword. So as you can see here, we're not going to start with function or anything else. We start with the func keyword, and that's going to describe a function that we're going to create. Then we have the name of the function that we're going to create, and this follows the same naming convention as any other variable in Go. So you're going to use Pascal case or camel case for the names of your functions, and depending on if you have an uppercase or lowercase determines the visibility of that function. So just like with variables, an uppercase first letter is going to be published from the package so anything else can use it, and a lowercase function name is going to be kept internal to the package. Now after the name of the function, we have these matched parens here. Now we'll see as we get into parameters what these are for, but this is required syntax after the main function. So even if you don't take any parameters in your function, you have to have these matched parens. And then the actual body of the function is contained within these curly braces here. Now, there are a lot of holy wars in a lot of languages about where these curly braces should go. So some languages put them here, some languages put them down here, some languages like to indent them. There's all sorts of different conventions about where to put these curly braces. Well, in the Go language, there aren't any arguments because this is the convention that is enforced by the compiler itself. So you have to put the opening curly brace on the same line as the func keyword, and then the closing curly brace generally has to be on its own. Now there are a couple of situations where you can have that closing curly brace combined with a couple of other parens, and we'll talk about that a little bit later in this video, but generally speaking, when you're defining a function, the closing curly brace has to be on its own line. Now with functions defined like this, the execution path is static. We can't actually influence what our function's doing from the outside, because we're not passing any information into it. So if we do want to pass information into it, then we're going to provide what are called parameters into the function. So let me just drop an example that uses parameters. And you see here, our main function is now calling into another function called sayMessage. And that sayMessage function takes in this parameter MSG that's of type string. So when you're defining a function that takes parameters, the parameters go between these two parentheses here, and they're described like any other variable declaration except for you don't need the var keyword. So you're going to have the name of the parameter and you're going to have the type of the parameter. So then when we want to call that function, we have to pass in the value for that parameter, and that's called an argument. So we're going to pass in the argument hello go, and then inside of our function we're printing out the message that gets passed in, and so when we run this, we see that hello go prints out as a result. Now this MSG parameter isn't special in any other way than the fact that it's passed into the function. It's treated as a local variable just like any other local variable that we might create. So if we created another variable here, and we said hello go, that's treated exactly the same way as our MSG variable. So the only difference between the two is the MSG variable can be passed in from the outside, and of course that greeting variable was created locally. Now you aren't constrained to just pass a single parameter in. You can actually pass multiple parameters in. So if I drop in this example, we can see that in action. So here I've extended the sayMessage function to take two parameters. So I've still got the message parameter that's of type string, and then I've put this comma here, and I've added another parameter, and that's going to be an index, and that's going to be of type integer here. So as you can see, we can pass as many parameters as we want. We're just going to provide a comma delimited list of those parameter names and their types. So then when we call the function, we're going to pass in one value for each one of those parameters, and they have to be in the same order that they're declared. So the first argument that we're going to be passing is the string hello go, which is going to match this MSG variable. And then we're going to pass in the I that's going to be the loop counter here, and that's going to be passed into this IDX parameter. So then in this function, we're just going to print out the value of the message, and then we're going to say what index we receive. So when we run this, we see that the message prints out 5 times, and we get the same message, but the index variable changes because we're passing in a different value every time we call the function. Now often when you're defining a function, you're going to pass in multiple parameters of the same type. So you're going to be tempted to have syntax like this. So in this example, we've got a slightly different function. So instead of a generic say hello, we're going to have a say greeting function, and we're going to provide the greeting that we're going to have and the name of whoever it is we're going to greet. So in this case, we're passing in the string hello and the string Stacy. So when we run this, we're going to say hello to Stacy. Now, since these types are the same, the Go compiler actually provides us a little bit more syntactic sugar because this is a little bit more verbose than is strictly necessary. So instead of specifying the type every time, we can actually just specify a comma delimited list of variables and then the type at the end. And what the compiler is going to do is it's going to infer that every variable that's in that comma delimited list has the same type. So when we run this, we actually get exactly the same execution, but we just have a little bit more terse syntax. Now, so far, we've been passing parameters in as value types. If you remember from our last discussion, we were talking about pointers, and notice that I don't have any pointers in our function signatures right now. So let me drop in this example here, and then we can start playing around with the difference between passing in values and passing in pointers. So when I have this example here and I run it, we get exactly the same output that we had before, but I've got some variables that I'm using to pass in as arguments to this function. Now, what do you think is going to happen if I change the value of one of these variables inside the function? So for example, if I change the name variable to Ted, and let's go ahead and print that out just to verify that it printed. And then what do you think is going to happen if I print the same variable out again right here? So I'm passing in the name variable by value. So that means that the Go runtime is going to copy the data that's in this name variable and provide it to here. So what we would expect is when we change the value of the name variable right here, it should have an effect and we should print Ted out here. But since this is a copy of the name variable, we actually shouldn't have any effect out here. So if we run this, we see that in fact that is true. So this is a safe way to pass data into a function. You can be assured by passing by value that the data is not going to be changed when you pass it in. Now if I change this to passing in pointers by adding a pointer here, and then passing in the address of these variables right here, and then dereferencing the pointers right here, then let's see what's going to happen. Actually, I need to add another dereference right here, and now we're passing pointers to our variables around in our application. So now, instead of working with a copy of the name variable, we're working with a pointer to the name variable, and so when we run this, we actually see, looks like I missed a dereference operation right here, and now we see that we have in fact changed the variable not only in the scope of the function, but in the calling scope as well. So by passing in a pointer, we have in fact manipulated that parameter that we passed in. Now why would you want to do this? Well, there's a couple of reasons. First of all, a lot of times our functions do need to act on the parameters that are passed into them, and so passing in pointers is really the only way to do that. The other reason is passing in a pointer is often much more efficient than passing in a whole value. Because right now we're passing in simple strings, and strings aren't that large in Go, so passing in copies versus passing in pointers is pretty much going to be the same in terms of performance. However, if you're passing in a large data structure, then passing in the value of that data structure is going to cause that entire data structure to be copied every single time. So in that case, you might decide to pass in a pointer simply for a performance benefit. Now, you do have to be a little careful when you're passing in pointers because, of course, you can inadvertently change that value, and so you can cause some issues for yourself. Now, just to remind you of something else that we talked about in the pointer discussion, if you're working with maps or slices, then you don't really have this option, because since those two types have internal pointers to their underlying data, then they're always going to act like you're passing pointers in. So just be careful when you're using those data structures, because you can inadvertently change the data in your calling function when you're manipulating them within the called function. The last thing that I want to talk about when we're working with parameters are what are called variadic parameters. So if I drop in this example here, we can see an example of a variadic parameter. So in this case, I've got a generic sum function that I'm creating here, and I'm passing in the numbers 1 through 5. Now, I'm not receiving 5 variables here. Instead, I've got one variable here, and I've preceded its type with these 3 dots here. So what that's done is that's told the Go runtime to take in all of the last arguments that are passed in and wrap them up into a slice that has the name of the variable that we have here. So then inside of the sum function, we're going to print out what that values object is, just so we can see that, and then we're going to go ahead and add up all the values in there. So since it's going to act like a slice, we can use a for loop and range over those values, and then we're going to print out the result of that. So when we run this, we see that we do in fact have a slice that's printed out. The sum is 15, so we got that result printed out properly, and there's no problem at all. Now, when you're using a variadic parameter, you can only have one, and it has to be the last one. So if I, for example, want to have a custom message string, I can pass that in, and then pass that in here, and then replace this, and this still works just fine. However, I couldn't, for example, put the message parameter as the last parameter, because the runtime doesn't have the ability to understand where the variadic parameters end and where additional parameters would begin. So if you're using variadic parameters, you can only have one, and they have to be at the end. Okay, now it's nice to be able to pass data into our function, because now, depending on the different data that I pass in, I can change the behavior of the function. But it's also very useful to be able to use our functions to do some work and then return a result back to the calling function. So in order to do that, we're going to use what are called return values. So if I drop in this example, we see it's basically the same as our last example, but instead of printing the message in the sum function, we're returning the result out, and then the main function is actually working with that. So there's a change we had to make in our function signature. So right here after the parameter list and before the opening curly brace, I've listed the return values type. So in this case, I'm expecting to return an integer, so I just put int right here. Inside of my function, I'm going to use the return keyword, and then I'm going to return the value of the variable that I've been building up throughout the course of the function. So in this case, I declare the result variable here, I populate it in this loop, and then I return that result back. Now up here in the main function, I can catch that return value by declaring a variable and setting it equal to the result of this function. So s is actually going to be an integer type, because that's what's returned out of this function, and then I can work with that integer. So if I run this, I get exactly the same behavior that I had before, but now the sum function is more of a pure function. It doesn't care what I do with that result, it's just going to generate the result and return it back to the caller. Now, another feature that Go has that's actually pretty rare in a lot of languages is the ability to return a local variable as a pointer. So in our previous example, when we returned that result, Go actually copied that result to another variable, and that's what got assigned. But we can also do this. So if you look here, I'm returning a pointer to an integer now, and instead of returning the result, I'm returning the address of the result. And so s is now a pointer, so I've changed to a dereference operation. So if I run this, it works exactly the same way. Now, again, if you're coming from another language that uses pointers a lot and doesn't abstract away the differences between working on the stack and working on the heap, then this might freak you out a little bit. Because when we declare the result variable, it's actually declared on the execution stack of this function, which is just a special section of memory that's set aside for all of the operations that this function is going to be working with. So when this function exits, that execution stack is destroyed. That memory is freed up. And so in a lot of languages, this is not a safe operation, because now you're returning a pointer to a location in memory that just got freed. And so you've got no idea what value is going to be there. Well, in the Go language, when it recognizes that you're returning a value that's generated on the local stack, it's automatically going to promote this variable for you to be on the shared memory in the computer, what's also called the heap memory. So you don't have to worry about this value being cleared. The runtime is going to recognize that you're returning a pointer from the local stack, and everything is going to work for you just fine. And it makes a lot of things more convenient because within the function, we can work with this as a true value, so we don't have to worry about dereferencing pointers. And then just right at the end, we can return the address of the result, and the runtime makes it all work for us. Another thing that we can do in the Go language, and this isn't done very often, but there are cases where it is valuable, is using named return values. So if I drop in this example here, notice that I've changed my return value now. I've got a set of parentheses here, and then I've got a name for the return value and a type for it. So when you do this, this is basically syntactic sugar for declaring a result variable. So this variable is going to be available in the scope of our sum function, and then that value is going to be implicitly returned. So we can work with that result variable right here within our function, and then we don't have to specify the name of the return variable down here on line 17. We just have to tell it to return. So when we run this, we see that once again we get exactly the same behavior, but the body of our sum function is actually quite a bit cleaner because we don't have to do the maintenance of instantiating this result variable. Now this is actually not done very often in the Go language, and my suspicion is because it can be a little bit confusing to read, because your return variables are declared way up here at the top of the function, and your actual return is down here at the bottom. So if you're reading this code and you're trying to figure out what this function is actually going to return, you have to come all the way back up to the function signature. So this can be a very valuable technique to use, but I would be very careful with it, because if you've got long functions, then named result parameters can actually be more confusing instead of less confusing. So you have the option there, pick whichever one makes the most sense for your application. The last thing that I want to talk about with return values is the fact that we can do multiple return values from a function. So in order to show you why this is valuable, let's take this example here. So I've created a simple divide function that takes in two parameters, a and b, that are float 64s. It's going to divide them, and it's going to return that result back. So if I run this, I get 1.66666, like you might expect, and everything's fine. But what happens if I pass in a 0 here? Now when I run this, I get an unknown result. I get a positive infinity result, and I can't work with that in my application. So I'm going to probably cause some sort of a failure down the line. So in a lot of languages, the only thing we could do is throw an exception or panic the application in Go when we detect that there's this invalid value for the parameter b. So I guess we could do that. We could add some kind of logic here. If b equals 0.0, then we're going to panic, and we're going to say cannot provide 0 as second value. And that would work. But keep in mind, when we talked about control flow in Go, we don't want to panic our application as a general course of action, because panicking means the application cannot continue. Now, in fact, this application cannot continue if somebody provides a value of b. But it's reasonable to assume that we might pass 0 in for this b parameter occasionally. So instead of doing this, what we actually want to do is return an error back, letting the calling function know something that they asked it to do wasn't able to be done properly. So instead of doing this, we're actually going to add a second return variable. So to do that, we're going to add a paren here, and we're going to return an object of type error, and then close that parenthesis off. So we can return as many values as we want from a function, but this is a very idiomatic way of using the Go language. So we're going to return the intention of the function as the first return value, and then we're going to return an error object in case something went wrong. So in that case, what we're going to do is we're going to remove this panic, because we really don't want to be doing that, and we're going to return the first value. We're just going to zero it out because we can't do this operation, so we can't return anything meaningful. And then we're going to return an error object. Now you can generate one of those by using the errorf function, and we can say cannot divide by 0. So we're going to provide a value for that error, and then that's all we need to do here. So since we've returned out of this function in the error case, then if we get past it, we can continue as if our parameters are okay. And so in that case, we can actually do our operation, and then for the error value, we're going to pass nil because no error was present. And again, this is very idiomatic Go. We're going to return an error value if something went wrong, and then we're going to explicitly return nil if nothing went wrong. And then if you've read any amount of Go code, you've seen this quite a few times. We're going to check to see if that error, so we've got our standard if error is not equal to nil, and then we're going to put our error handling logic in here. So in this case, all we're going to do is print out the error and return from our main function. So we're going to exit our application, If we don't have that, then we're going to just print out the result of our calculation. So again, this is a very common pattern in Go. Inside of your functions that can generate errors, you're going to return the expected value and then an error as the second parameter. Then you're going to have a guard that's going to check for those error conditions. You're going to return as soon as possible from your function with the error value if an error is present. And the reason for that is we're going to try and left justify our code as much as possible, so we don't end up with these pyramids of doom where we're going to have else checks and we do all of our error checking at the bottom. We're going to do our error checking at the beginning and then return out as soon as possible. So if we do get past that, then we're going to be on our happy path and we're going to return out the result of our calculation and then a nil error. Up in the calling function, we're going to have the standard test to see if error is not equal to nil. If it isn't equal to nil, then we're going to process that error because now we've got something we're going to have to deal with. And then again, we don't have an else block here. We just continue moving on. We're going to make sure our error handling logic either recovers from the error or exits out of the function, and that way we can keep our main thread of execution left justified. So our main thread of execution here is we're going to call this divide function, and then we're going to print out the result. So any error handling should not force the main line of execution to be indented. So now if we run this, we see that I forgot to initialize my error parameter, so let's go ahead and add that. And this is something else I should talk about. When we're receiving multiple values out of a function call, we actually have a comma delimited list of those return values. So this D parameter is going to match up to this float64, and this ERR parameter is going to match up to this error parameter here. So now if I run, everything should work. And we see that we now get an error, cannot divide by 0. So our main function doesn't explode on us. We actually have something that we can work with. But if we put in a valid value, then we're on that other path of execution and we get the return value back out. Now, so far we've been treating functions as this special thing because we're always using this func keyword. We're declaring these at the top level of our application and we're working with them. But functions in Go are actually more powerful than that, because functions themselves can be treated as types. They can be passed around as variables, they can be passed as arguments into functions, you can get them as return values. Pretty much anything you can do with any other type, you can do with functions. So let's take a look at that a little bit. So in this example, I'm actually declaring a function on the fly, and this is called an anonymous function. Now we're going to continue to explore this over the next couple of minutes, but this is the simplest example I could come up with. So notice that I'm starting with the func keyword, I've got the parens for the parameters, I've got the opening and closing curly brace, but I don't have a function name here. So when you're doing this, this is what's called an anonymous function. And this is the basic structure of a function when you're not working with functions in this traditional scope, but instead you're working with functions as types. So inside of my function body, I'm printing out the message hello go, and then I've got accompanying my closing curly brace, these parens here. Now these parens here are basically going to invoke this function. So this is an immediately invoked function. I'm defining it and executing it at exactly the same time. So when I run this, it actually does execute that function and we get the value hello go printed out. If I don't have these parens, then the compiler is a little confused. It doesn't know what to do with this function. It's just defined, but it's never used anywhere, so it fails a compilation check. But if I do invoke that function immediately, then I get this behavior here. Now, why would you use an anonymous function like this? I actually have no idea why you would use an anonymous function like this. I mean, there can be situations where you can declare variables inside of here. So if I declare a message variable here and I set that equal to this string and then print that out, that can be valuable because you're actually generating an isolated scope. So this message variable is not going to be available in the main function. It's only going to be inside of this anonymous function here. Now, another place that you might use this is if we've got a for loop. So if I start up a simple for loop and I'll just count up to 5 and increment by 1, see if I can do this on the fly here. And then I come in here and I actually print the value of I out. So I'll get rid of this message here and I'll print out I. You're going to get a little bit of strange behavior. If I run this, this works okay. But as we start getting into asynchronous code, things are going to start behaving a little bit oddly. So we do have access to this I variable because we're in the scope of the main function, and so inner functions can actually take advantage of variables that are in the outer scope. But the problem is, if this function is actually executing asynchronously, then this counter variable is going to keep going, and we may actually have odd behavior here. So the best practice is actually to provide a variable inside of here and actually pass that I variable. And what that's going to do is we're not going to be reading from the outer scope anymore. We're going to be passing that into the function execution. And that way, even if this is running asynchronously, we're going to print out the value correctly. Now, this works correctly in the playground the way that we have this right now, because we actually aren't doing anything asynchronously. This is all synchronous execution. And so we are safe to use this outer counter, but it's not good practice to do that. Instead, it is best practice to pass in that counter variable if you need that in your inner function. That way, changes in the outer scope aren't reflected on the inner scope. Now, taking this a little bit farther, we can work with functions as variables, like I said before. So in this case, I've declared an anonymous function, and I've assigned that to this variable f, and then I can execute f by just invoking it like any other function. So if I call that, we see that we do print hello go out. So now that I've got this function defined as a variable, it's free to pass around my application. Now you might ask yourself, what is the signature for this function? So let's go ahead and go through that. So if I get rid of the short syntax and extend this out a little bit, then I'm going to start with the var keyword. And since this is a very simple function, the type is just like this. We have the func keyword and then an open and close parenthesis. So the parameters normally go in here. I don't have any parameters here. I don't have any return types. So the type signature for this variable is simply func with two parens there. So if I run this, that works just fine. Now we can go a little bit more complicated, and I'll drop an example of that in just to show you how that's going to look. So in this case, I'm declaring a function signature for a divide function. That's going to take in two floats, and it's going to return a float and an error. And you see this is the syntax for that. So we pass our parameter types in here, and then we have the return types in parens as well. If you have just a single return type, then you don't need these parens. We could just put the type there like that. But we do have that error type that's coming back, so we do need to include that. And then when I initialize that variable, I'm going to set it equal to an anonymous function that takes a and b. And this is exactly the same divide function that we had before. And I can call that exactly like we had before. So when I run this, it has exactly the same behavior as the last example we did with the divide function, but now we have the divide function declared as a variable, and we're working with it exactly the same way as when we declared it as a function. Now the difference between this and when we had the divide function declared globally is if I try and call it up here and run the application, notice that I get an error, because in this case, the function divide hasn't been declared yet because it's declared as a variable, and so I can't work with it yet. So that's just something to be aware of. If you're going to be working with functions as variables like this, make sure that they're defined before you actually try and execute them. Okay, the last thing that I want to talk about with functions today is working with what are called methods, and there's a couple things to talk about with those. So let me just drop in an example that shows that, and we can walk through this and then see what it's going to do. So in this example, I've got a struct called greeter. That greeter struct has two fields, greeting and name, and then I've got this method on it, and we'll come back to this in a second. So in my main function, I'm declaring a greeter struct, and then I'm calling this function, preceding it with the struct that I have here. And this is how we're going to do method invocation. So we call the method just like we were accessing a field, except for we have the parens here where we can pass some arguments in. Now my method declaration down here looks a lot like a function, except for it's got this odd bit right here. And this is what makes this function into a method. So a method is basically just a function that's executing in a known context. And a known context in Go is any type. Now it's very common that we can use structs, but you can use any type. So we can make a type for an integer. So maybe we have a type for an integer called counter, and then we can add methods onto that counter type and work with those. So when we declare that method, we're actually going to get access to that type right here in this part. So what's going to happen when we call the greet method is the greet method is going to get a copy of the greeter object, and that's going to be given the name G in the context of this method. So then when we print out, we can access the fields on that greeter object, so we can print out the greeting and the name. So when we go ahead and run this, we see that we get hello go printed out, and that's the basics of a method. So methods are basically the same as functions. They just have this little bit of syntactic sugar that's providing a context that that function is executing in, and when we do that, we call that a method. Now when we use this syntax right here, notice that we're specifying greeter as a value type. We don't have a pointer here. So this is what's called a value receiver. The received object in this greet method is the value greeter. So what that means is just like any other time that we're working with values, we are getting a copy of the struct. We're not actually going to get the struct itself. So if I change the value of the name field here, and then I print the name field out up here, so I say the new name is, and then I print the name field out, then it's no big surprise that even though I assigned an empty string to the name field here, up here in the main function, it didn't have any effect. Because down here in this method, we're operating on the copy of the greeter object. We're not operating on the greeter object itself. So again, that's very valuable if you want your methods to be able to access the data of their parent type without being able to manipulate it. Just keep in mind there is a cost with that. So if this greeter object was a very large struct, then we would be creating a copy of that struct every time we invoke this method. Now, as you might expect, there's another option that we have here, and that is to pass in what's called a pointer receiver. So if we make this a pointer and run the application again, now we're actually able to manipulate that underlying data. So we're going to print out hello ghost, so the method operates in exactly the same way, and we don't have to change the format here because we do have that implicit dereferencing of pointers that's working for us. But now when I change the value of the name field and print the name field out up here, we do in fact see that we've been able to reassign the value of that field. Okay, so that covers working with functions in the Go language. Let's go into a summary and review what we've talked about. In this video, we talked about functions and how to use them in the Go language. And we started out by talking about the basic syntax of a function. And we saw that this is about as simple of a function as we can get. So we start with the func keyword. We have a name for that function. And again, if that first letter is uppercase, then that function is going to be published and allowed to be executed from outside of the package. But with a lowercase first letter, it's going to be kept internal to the package. Then we follow with a matched set of parentheses. And then we have an open and closed curly brace. Now the open curly brace has to be on the same line as the func keyword, and the closed curly brace has to be on its own line after the final statement of the function. Then we moved on to talk about parameters, and parameters allow us to pass data into the function to influence how that function executes, basically providing some variables for the function that are passed in from the outside. So we talked about how parameters are passed in as a comma delimited list of the name of the parameter and the type of the parameter. So we see here we're passing into the foo function two parameters, the bar parameter that's of type string and the baz parameter that's of type integer. Parameters of the same type can be comma delimited and the type can be listed at the end there. So in this case we're passing in bar and baz as parameters, and both of those are going to be of type integer. When pointers are passed in, the function can change the value in the caller. So by default, we're going to be passing in the values themselves. And so the Go runtime is going to be copying that data and passing it into the function. So any changes that are made inside of the function aren't going to be reflected in the caller scope. However, if you pass in a pointer, then you are going to be able to manipulate the value inside of your function, and that will have an effect in the calling scope. So the only exception to this rule is when you're working with slices and maps. Since they work with internal pointers, any changes inside of the function to the underlying data is always going to be reflected inside of the calling scope. We also talked about how you can use variadic parameters to send a list of the same types in. So it must be the last parameter in the parameter list. It's received inside of the function as a slice. And you see an example of the syntax right here. So we've got the function foo. It has one parameter bar that's of type string, and then a parameter baz that's a variadic parameter of integers. So inside of this foo function, we're going to have a slice called baz, and that's going to contain all of the integers that have been passed in. Once your function finishes doing its work, a lot of times we want it to return a value back out. And in order to get that information back out, we're going to use return values. So if you have a single return value, all you need to do is list the type. So in this case, our foo function needs to return an integer. We can also specify multiple return values. So if we're going to do that, we need to put parens around the types that we're going to be returning. So in this example, we're going to be returning an integer and an error. And this is a very common pattern that you're going to see in Go applications, where we're going to have our functions return the intended value and then an error value that's going to let the caller know if anything went wrong. That way, the function itself doesn't have to determine whether the application needs to panic or execution can't continue. It just knows it wasn't able to do what it was asked to do, and then it can delegate what that error means to the application to the calling function. You can also use named return values. So when you do that, instead of just providing the types in the return list, you're going to provide the name of that return value. So when you do that, the runtime is going to initialize that value for you to the 0 value for that variable. And when you use the return keyword, all you need to do is enter return on its own. Go is going to find the current value of those return variables, and that's what's going to be returned out of your function. Another special behavior of Go is you can actually return the addresses of local variables as return values, and those are going to be treated properly. So when you do that, those variables are automatically promoted from local memory or stack memory up into shared memory or heap memory, so you don't have to worry about those values being cleared out as the function's stack memory is reclaimed. We then started talking about anonymous functions, and we talked about a couple of different uses for those. So we have this immediately invoked function, which really isn't used too often in the Go language, but it's as simple of an anonymous function as I could get. The only potential advantage that you have here is that you can create an inner scope, so local variables that are created inside of this anonymous function aren't going to be available outside, but I haven't seen that very often. It's not going to be very often that you're going to need to use this kind of a function. Then we also talked about how we can take that anonymous function and actually assign that to a variable. So in this example, we've got the variable a assigned to the value of that function, and then we can invoke the a function just like any other function. The only difference between this and the normal declaration of a function is that the a function can only be invoked after it's been declared. So when you declare a function using the traditional syntax, it's actually declared at the time that the package is initialized, and so it's always available to you. When you're using this syntax, you have to make sure that a is initialized before you can call it. Extending on that discussion about the ability to assign functions to variables, functions are types just like any other type in the Go language. Anytime you can use a primitive or a slice or an array or a map, you can use a function. So you can assign them to variables, you can use them as arguments, they can even be return values from functions. Then we also talked about how, since a function is a type, we have to have the ability to create a type signature. So if you're declaring anonymous functions, it's often most convenient just to use that := syntax and declare your anonymous function, and the type is going to be inferred. However, if you're using a function as a parameter to another function, or as a return value from a function, then you're going to need to specify that type signature. So we see an example here. In this case, we've got the definition of a function f, and that function is going to take 3 parameters, 2 strings and an integer, and then it's going to return an integer and an array type. So it's basically the same as when you're declaring a function normally. The only difference is we don't have the names for those variables, because those names will be provided when we actually implement the function. We just need to know the types that are coming in and the types that are coming out at this point. The last thing we talked about were methods, and how a method is a special type of function that executes in the context of a type. Now, a type doesn't have to be a struct, although that definitely is a very common use case for methods. You can actually attach a method to any custom type. So you can create a type of an integer, and then you can add methods onto that integer. When we create a method, we're going to use a modified version of the basic function syntax. So before the name of the function and after the func keyword, we're going to provide another set of parens. We're going to provide a local name for the type that's going to receive that method, and then we're going to follow that with that method type. Now that variable is what's called the receiver for the method. So in this case, our G variable is what's called a value receiver, which means we're going to get a copy of that greeter object, and that's going to be passed into the greet method. However, we can also use what are called pointer receivers. So by adding an asterisk in front of that greeter type, the method is going to change. So instead of passing a copy of the greeter, we're going to get a pointer to the greeter object in there, and then any manipulations we make to the greeter object in the greet method are going to be reflected throughout your application. Now that's very powerful if you need the method to be able to manipulate the state of the object. It's also much more efficient if you're dealing with large structures, because instead of copying the entire structure, it only has to copy a pointer, and that's normally a much more efficient operation. I want to talk about one of the coolest features of the Go language, and that is interfaces. Now I know that interfaces are normally considered pretty humble features and they sit in the background. It's much more fun to talk about Go routines and channels, especially when you're learning the Go language. But I would argue that the way interfaces are implemented in the Go language are potentially one of the reasons why Go applications tend to be as maintainable and scalable as they have proven to be. So we're going to start this conversation like we start every conversation by introducing the basics. So we'll learn what an interface is and how to use them in the language itself. Then we'll move on to discuss how to compose interfaces together. Now, just like in other high-level languages such as Java or C#, we can actually make interfaces of interfaces, and we'll talk about how to do that and why that's a very good thing to do when you're writing your Go applications. Then we'll talk about type conversion. Now, we've touched on this a little bit before in a previous video, but when we talk about interfaces, things change a little bit, and it's worth revisiting the topic. Along the way, we're going to talk about the empty interface, which is a very useful general construct that we're going to deal with in our programming. We'll also revisit type switches, which we've talked about before, and we'll revisit them in the context of our interface discussion. Then we'll talk about how to implement interfaces, and there's actually 2 different ways that you can do that. One is by implementing with a value type, and one is by implementing with a pointer. And we'll talk about some of the subtle differences that you're going to run into as you implement interfaces with these 2 different types. And then finally, we're going to talk about some best practices that have been discovered over the last few years of working with the Go language about how to use interfaces in your actual production applications. Okay, so let's get started by learning the basics of using interfaces in Go. So to start our discussion about interfaces, I'm going to actually build our first application up a piece at a time. Now, often I just drop in code and talk about it, but I want to take this one step at a time so that we're working together and understanding what's going on. So the first thing that we're going to do is we're going to introduce our first interface. So interfaces are a type, just like structs or type aliases. So we're going to start with the type keyword, then we're going to enter the name of our interface, and then the type that we're creating is a type interface. And then we're going to surround the definition of this interface with curly braces, just like we do when we're defining a struct. Now with a struct, we would add in here the data that we want that struct to hold on to, because structs are ultimately data containers, and so that's how we work with them. Interfaces don't describe data, interfaces describe behaviors. So instead of entering a bunch of data types that we're going to be storing inside of our writer interface here, we're actually going to be storing method definitions. So I want to create a write method here, and this is actually an interface from the IO package. We're just going to be working with it here as if we created it. But this is exactly the same interface that you would find in the IO package under the writer interface. So this method is going to accept a slice of bytes, and then it's going to return an integer and an error. Now in the writer interface, the way this works is anything that implements this interface is going to take in that slice of bytes, write it to something. That something might be the console, it might be a TCP connection, it might be the file system. We don't know. We just know that we're writing a slice of bytes to something. And then the integer and error that get returned, of course the error is there in case something goes wrong with the write operation, and the integer is normally the number of bytes written. So now that we have the interface defined, let's go ahead and implement it. So we're going to implement this with a console writer implementation, and that'll be a struct. And that's all we need to do with the struct definition. Now, if you come from another language, you might be looking for an implements keyword or something like that. Well, in Go, we don't actually explicitly implement interfaces. We're going to implicitly implement the interface, and we're going to do that by actually creating a method on our console writer that has the signature of a writer interface. So let me just drop that in, because if I try and type all this out, I will screw it up and then I'll have bugs that I have to go through. So it's much easier just to drop it in. But notice what I've done here. I've got a method on my console writer called write. So it's got the same name as my writer interface. It's accepting a slice of bytes, and it's returning an integer and an error. Now the implementation is whatever I want it to be. Now in this case, all I'm going to do is convert that byte slice into a string and print it out to the console to keep things easy in the playground. But I could have my writer do whatever I want. So what's the value of doing this? Well, the value of doing this is up in my main method, I can actually create a variable that's of type writer, and let me just drop that code in and format it, and set that equal to a console writer instance. So the W variable here is holding a writer, which is something that implements the writer interface. I don't actually know the concrete type though. So when I call the write method down here on line 9, I know how to call that because that's defined by the interface, but I don't actually know in my main function what's being written to. That's the responsibility of the actual implementation. So I could replace this with a TCP writer, I could replace it with a file writer, I could replace it with any other kind of writer, and so I get what's called a polymorphic behavior. Line 9 doesn't care what it's writing to. I specify that behavior before that, but then anything that's going to use this W object just knows that it can write to it, and so it can take advantage of that behavior. So if I go ahead and run this application, you see that I do get Hello Go printed out to the console, just like I would expect. So the key takeaway here as we're learning the basics of interfaces is this concept of implicit implementation. So what that means, for example, is if you need to wrap a concrete type and somebody hasn't published an interface, you can actually create an interface that their type implements. So we did it the other way. We created an interface and then we created a concrete type that implemented it, but there's nothing to say we can't go the other way around. We could, for example, go to, if I travel to golang.org and go into packages, this is actually something that I just ran into in order to test SQL database connections. So if I come down to the database package and go into the SQL package, if we look at this, notice that the DB type is a struct. So we don't have an interface here. So if our Go application is talking to a SQL database, we've got concrete types all over the place. So for our transactions, we're interacting with this DB object. Everything that we're doing, sending SQL statements, making queries, are all through this concrete DB object. So how do I test that without a database? Well, the way that you test that without a database is you actually create an interface that replicates this method signature, and the DB object from the SQL package will automatically implement it. So I don't have to worry about creating interfaces at design time if I don't need them for myself, because consumers of my library or whatever I'm creating can always create interfaces later, and their interfaces can be shaped to exactly what they need for their application. Now, another thing that I want to talk about before I move on here is a naming convention. Now, obviously, the name of the interface should represent what that interface is going to be doing for you. And there is one special case. If you've got single method interfaces, which are very common in the Go language, then the convention is to name the interface with the method name plus ER. So if we're defining an interface like we have here with the write method, then the interface name should be writer. If we're going to create an interface with a read method on it, then the interface name should be a reader. Now, if you got more than one method in the interface, things can get a little bit more challenging, but at the end of the day, you should name your interface by what it does, and in the case of a single method interface, just add ER onto the end of the method name. Okay, now in this example, we used a struct, which is probably one of the most common ways to implement interfaces, but you don't need to. Any type that can have a method associated with it can implement an interface. And as we've talked about before, any type can have methods associated with it. So in order to demonstrate that, let me just drop in this example here. Now in lines 16 through 18, I've defined a new interface called incrementer, and that increment is going to be a method that only returns an integer. So it's going to increment something. So whatever we're going to implement this thing with is going to increment values. So down here on line 20, I defined a type alias for an integer called an int counter. And then I've added a method to that custom type on lines 22 through 25, and that's going to be my implementation for the incrementer interface. So the method name is called increment, and it's going to return an integer. Now in this case, look at what I'm doing. I'm actually incrementing the type itself. Since I've got a type alias for an integer, it's a number, so I can go ahead and increment that, and then I'm going to return it as the result of this method call. So I've actually got a type defined on an integer, and the integer itself is storing the data that the method is using. So up here in my main function, I'm going to go ahead and create that integer counter, and I have to cast an integer to an int counter in order to do that. That's what I'm doing here on line 8. And then I create my incrementer and assign that to a pointer of the myInt object, and we'll talk about why that has to be a pointer toward the end of this video. And then I'm just going to loop from 0 to 9, and I'm going to print out the value of the increment method every time I call it. So if I go ahead and run this, I see no big surprise, I get the values 1 through 10 printed out. So what's the takeaway here? Well, you don't have to use structs to implement interfaces. You can use any kind of custom type. Now, I couldn't add a method directly to the int type because the int type isn't under my control. That's defined in another package, and as a matter of fact, that's a primitive type and you can't modify it. But any type that I do have control over that I can create, I can add methods to it, and if I can add methods to it, I can implement interfaces with it. Now, the next thing that I want to talk about is how to compose interfaces together, because this is another very powerful concept in the Go language and is one of the keys to scalability. Because if you remember, I mentioned a little while ago, single method interfaces are very common and very powerful in the language because they define a very specific behavior, but by having a single method, they don't have a lot of opinions, and so they can be implemented in a lot of ways. So for example, the io.writer interface is one of the most common interfaces in the entire Go language because all it does is talk about how to write to things. And we write to things all the time. So by taking as little opinion as possible, we actually make the interface very, very powerful and very, very useful. So let me go ahead and paste this example here, because what happens if we need more than one method, but we can decompose the interfaces down? So in this case, I've created an interface that's composed of other interfaces. So I've got my writer interface that we started the video with, and then I've added this closer interface that just has a close method on it and returns an error, just in case something happened when we tried to call this method. Now the writer closer interface is actually composed of the writer interface and the closer interface. And this is done exactly the same way that you do embedding with structs. We're just embedding interfaces within other interfaces. So the writer closer is going to be implemented if an object has this method on it and this method on it. Then we can treat that as a writer closer. So as an example, I've created this struct here, a buffered writer closer. Now, I'm not saying that this is an efficient way of doing things. This is just an example of how you might use this writer-closer interface in a way that runs in the playground easily. So in this case, I've got my write method that I'm going to be implementing. And what I decided to do is I'm going to write out whatever gets sent into the buffered writer-closer. I'm going to print that out to the console in 8-character increments. So that's what all this code is doing. When you pass data into the write method, it's going to store that in this internal buffer that the struct defines. And then as long as the buffer has more than 8 characters, it's going to go ahead and write that out, but it won't write anything out if it's got less than 8 characters. So we're basically buffering the data that we're sending in. And then down here in the close method, I've got to implement that too. And so what we're going to do there is we're going to flush the rest of the buffer. So I'm pulling the next 8 characters out, and I'm going to write that out to the console and keep doing that until the buffer is empty. Okay, up here in the main method, I simply create a writer-closer variable and define that using the new buffered writer-closer function. And just to show you that, I didn't talk about it. That's down here at the bottom. That's just a constructor function that's returning a pointer to a buffered writer-closer. And I need to do that because I need to initialize this internal buffer to a new buffer. So I have a constructor method there just to make sure that everything's been initialized properly. So if I come back up to the main function and look at that, then I'm going to call the write method, and I'm converting the string hello YouTube listeners, this is a test, over to a byte slice because that's what the write method expects. And then I'm going to call the close method. So if I go ahead and run this, you see that I get the message printed out to the console in 8-character chunks, and eventually I get all this printed out. But if I comment out this last method call here, you see that I don't get the a-test part of the string because that's actually a partial. And so we didn't get that full 8 characters that's required for the write method to print it out. And so I didn't actually flush the buffer. Okay, so I know that may be a little bit of a complicated example to show a fairly simple thing, but I just wanted to show you this is how you can compose interfaces together. And as long as you implement all of the methods on the embedded interfaces, then you actually implement the composed interface as well. The next example that I want to talk about is how we can do type conversion. So I'm going to go ahead and replace my main function here with this code here. Get rid of the extra curly brace. Actually, I'm going to get rid of this too. I guess I pulled in the whole function signature. And then I've made a little bit of a change down here on line 13. So lines 9 through 11 are our original implementation, where we're creating the new buffered writer-closer, we're writing a string out, and then we're calling the close method on it. But on line 13, I'm actually doing a type conversion. So using this syntax here, where I've got an object, dot, and then in parens, I've got a type that I'm going to try and convert this variable to, and then I can assign that to a variable such as this BWC variable right here. Now, if that succeeds, then everything's fine, and I can go ahead and work with it. Now, there's nothing useful I can do with this, but I'm just printing out the variable because I have to use the variables in Go, so I'm just going to go ahead and print that out. So if I run this, I see I get exactly the same output I had before, but now I get the memory address of this buffered writer-closer. So that type conversion succeeded, and therefore I can work with this no longer as a writer-closer, but as a buffered writer-closer. So for example, if I needed to access the buffer directly, then I would be able to do that now, whereas with the writer-closer, it's not aware of the internal fields of a specific implementation, and so I wouldn't have access to that data. Now there is a problem, however, if I import the I/O package and try and convert this to a type that it doesn't implement. So for example, if I try and convert this over to an I/O reader, which is another interface, and that I/O reader interface requires a read method on it. So if I try that now, let's go ahead and run that, and we see here we've put the application into a state that it can't manage. And so what it does is what every good Go program does when it can't figure out what to do, it panics. And the panic message is interface conversion. It can't figure out how to cast a buffered writer-closer into an I/O reader, and so it's going to fail on us. Now it does give us some useful information about why it couldn't do that. It says it's missing a method read, and then it's going to give us a stack trace letting us know where that error occurred. Now this isn't really great, because sometimes we need to try and convert an interface into something else, and we're not sure if it's going to work or not. So it's not going to be good for our application to be panicking all the time, because then we're going to have recovers, and we're going to be using that as a primary control flow concept, and we want to avoid that in the Go language, because panicking is pretty expensive, so we need another way around it. Well, we just so happen to have another way around it. And so I'm going to show you that. All we need to do, let me rename this variable because BWC doesn't make sense for a reader anymore. I'm going to paste this code in. So I'm going to now try and cast it to a variable called R. I'm going to do the same type conversion, but now I'm using this comma OK syntax. So we've seen this before when we were trying to pull a value out of a map and we weren't sure if it was there or not. Well, we have the same ability with type conversion. If we add a comma OK, this is going to be a Boolean result, and then we can test against that to see if we can work with it. So if the conversion succeeds, then we're going to get an OK value back out. If the conversion fails, then we're going to get the 0 value of whatever type we were trying to convert to. So an IO reader is an interface, and so its 0 value is going to be nil. So if we go ahead and run this now, we see that our conversion failed, but our application didn't crash. If we switch this back to a pointer to a buffered writer closer, let me go ahead and drop that in, and we run that, we got to drop out our package here that we're no longer using. And then we see that we're back to having things successfully converted, and we could work with that however we needed to. So this is really important to be aware of, especially if you're not sure if you're going to get a pointer or a value type. So for example, it would be really easy to write this and have a problem because we implemented the interface with a pointer, not with the value itself. And so we can't actually do the conversion to the underlying value type. So let's go ahead and run this again. We see that that all works. And one more thing I want to show you. Let me just pull this error back up again. You notice that the reason this type assertion failed is because buffered writer closer does not implement writer closer. Now that might seem a little strange to you because our buffered writer closer has a write method and it has a close method and they have the right signature. So for some reason this works when I ask it to convert it to a pointer, but it doesn't work when I ask it to convert it to the underlying value. Now we'll come back in just a second and talk about why that happens, but I want to finish our discussion of type conversions first. So stay tuned and we'll talk about why that works the way it does. So the next thing that I want to talk about is something called the empty interface. Now the empty interface is exactly that. It's an interface that has no methods on it. And we describe that using this syntax here. Now this isn't a special symbol, this is just an interface that we're defining on the fly and we don't have any methods on it. So it's called the empty interface, but there's nothing special about it. We could create this as the empty interface exactly the same way by just deleting the method out. And that's an empty interface now. So you see it like this all the time. Just be aware, there's nothing special about this. It's just an interface defined on the fly that has no methods on it. Now the nice thing about the empty interface is everything can be cast into an object that has no methods on it, even primitives, because, well, an integer has no methods, and so it can be cast to the empty interface. And so this can be very useful in situations where you've got multiple things that you need to be working with, but they aren't type compatible with one another, and you need to apply some logic later to figure out exactly what you received. But we do have a problem with the empty interface. Because we now have this myObj variable that's defined as an empty interface, we can't actually do anything with it, because myObj has no methods that it exposes because it's an empty interface. So in order to do anything useful with a variable that has the type of an empty interface, you're going to need to do either a type conversion or you're going to need to start using the reflect package in order to figure out what kind of an object you're dealing with. So in this case on line 10, I'm actually trying to typecast into a writer closer, and I'm using the comma OK syntax to see if that worked. If it does, then I go ahead and call the write and close methods like I saw before, and then I've got this other type conversion that I've done down before just to keep things consistent. So if I run this, we see that I forgot to re-import the IO package, so let me go ahead and pull that back in. And we see that everything works as normal. So the empty interface is very common, but just keep in mind, it's almost always going to be an intermediate step. You're going to define a variable of the type empty interface, and then you're going to have to figure out exactly what you received before you can do anything useful with it. The last thing that I want to talk about in the context of type conversions are type switches. So I want to revisit that conversation from a few videos ago. And just to show you, we can do something like this. So in line 8, I've got a variable I that's defined as the empty interface, and I'm setting it equal to the integer 0. And then I'm going to use this switch block here, and I'm going to use this syntax. So I've got my variable name, I, and then I'm going to use this dot, and inside of parens, I'm going to put type. And so what this is called a type switch. So each of the cases in this type of switch are actually going to be a data type. So in this case, I'm looking to see if I've got an integer or a string, or I've got a default case, which is going to be handled by our application just saying it doesn't know what I is. So if I go ahead and run this, I properly identify I as an integer, so we execute this case here. If I put parens around this, then of course I is now going to contain a string, and so if I run that again, it identifies I as a string, and if I change this once again, maybe we can make this a Boolean, I got to spell true correctly, and I run that, then it has no idea what I is. So this is commonly paired with the empty interface in order to list out the types that you're expecting to receive, and then you would add in the logic of how to process those different types. Now, I promised you that we would come back and talk about that weird type conversion behavior where we could convert our writer closer into a pointer to a buffered writer closer, but we couldn't convert it into the value itself. So now I want to go through and have that conversation about why that happened. So let me just drop this code in. This is a much simpler implementation than what we had before. I've actually not really implemented these methods anymore in order to keep things as clean as possible for you to see. So all I'm doing is I'm going to create a MyWriterCloser, and that's down here as a MyWriterCloser struct with nil implementations for the methods. But I do have the methods implemented, so I can create this object as a writer closer. And then I'm just printing out the value of the variable just so we have some use for that variable so the Go runtime will actually compile and run this. And the interface for the writer closer is defined exactly the way we had before. So if I run this, everything works out just fine. However, what happens if I change the receiver of one of these methods to a pointer? Well, if I run this now, I get an error. And the reason that I get that error is it can no longer convert my writer closer into a writer closer interface. And it gives us an interesting message here. It says my writer closer does not implement writer closer. The write method has a pointer receiver. And this is the key to understand what happened with this. So when we define types and we assign methods to them, each one of those types has what's called a method set. Now, when you're working with the types directly, the method set is all of the methods, regardless of the receiver types, associated with that type. With interfaces, however, things change a little bit. When I implement an interface with the concrete value, so notice here I'm creating a MyWriterCloser. I'm not taking the address of a MyWriterCloser. I'm using MyWriterCloser directly. So WC is defined as holding the value MyWriterCloser. So the method set for a value, when we're talking in the context of an interface, is any method that has a value as the receiver. So the reason we're not implementing writer closer is because a write method no longer has a value receiver, it's got a pointer receiver. And so its method set is incomplete. Now we could fix this by using the address of operator and running again, and notice now everything works. And the reason for that is the method set for a pointer is the sum of all of the value receiver methods and all of the pointer receiver methods. So let's go through that again. When I'm implementing an interface, if I use a value type, the methods that implement the interface have to all have value receivers. If I'm implementing the interface with a pointer, then I just have to have the methods there, regardless of the receiver type. So the method set for a value type is the set of all methods that have value receivers, but the method set for a pointer type is all of the methods with value receivers as well as all of the methods with pointer receivers. So there's a couple of ways that we could fix this. Now in this case we don't need access to the underlying data, so we could just go back to a value receiver, and then this is going to work just fine. This is actually the initial example we had. If we have one method that's got a pointer receiver, however, we're going to need to switch that over to a pointer type. And notice I can actually remove this, and it continues to work, or I can make both of these pointer receivers, and this continues to work as well. So this is an important concept when you're implementing your own interfaces. If any of the methods require a pointer receiver, you're going to have to implement that interface with a pointer. If not, though, if all of the methods accept value types, then you can go ahead and use a value type if that's what you want, but you could also use a pointer. Okay, the last thing that I want to talk about are some best practices when using interfaces in your own Go applications. So let's take a look at those. Okay, when we're working with interfaces, there's a couple of rules and guidelines that I'd like you to keep in mind. And these have been developed over the last few years by the Go community and are generally accepted as some of the best ways to use interfaces if it's practical in your applications. The first is prefer many small interfaces versus large monolithic ones. Now, if you need large monolithic ones, that's fine. Go ahead and compose smaller interfaces together to make those. But the smaller you can make your interfaces, the more useful and powerful they're going to be. And that's not actually unique to Go. No matter what language you're working in, if interfaces are there, generally having many smaller interfaces is preferable in the long run to having a few monolithic ones. Now, some examples that are in the Go standard library are the io.writer interface, the io.reader interface, and the empty interface. Now, these are arguably three of the most powerful interfaces in the entire language. And if you think about it, writer has one method, reader has one method, and the empty interface has 0 methods. So it's interesting support to the argument that smaller interfaces are better, that some of the most powerful interfaces in the language contain 1 or 0 methods on them. Now, when you're working with interfaces, if you're coming from a language that has explicitly implemented interfaces, you're going to be very tempted to create interfaces and export those. So here's the guidance for that. If you don't need to export the interface yourself, so if you don't have any particular reason to do it, go ahead and don't. So there are some good examples of why you would want to do that, but often it's perfectly acceptable to export the concrete type. I'll take as an example the database/SQL package that we looked at earlier in the video, where we saw that the DB object was exported as a concrete struct, and it had all sorts of methods that pointed to other concrete structs. So you can't directly mock that out for testing right out of the box. However, by not exporting an interface, it allows you as the consumer of that struct to define your own interface that you can use for testing. And the beauty of that is, if you don't use every method on the DB object, your interface doesn't have to have every method on it. You can just expose the methods that you need. However, do export interfaces for types that you will be using. So if you're going to pull a value in, go ahead and accept an interface instead of a concrete type if at all possible. So this is going to be almost exactly backwards from how other languages consider interfaces, and the reason is that whole idea about implicitly implementing interfaces instead of explicitly doing it. So if you were working in Java or C#, you could not do this, because you have to define the interface before you implement the interface, because they're explicitly implemented. But since Go has implicit implementation, you can go ahead and defer the creation of the interfaces until exactly when you need them. So if you're creating a library that other people are going to consume, you can define the interfaces that you accept, and then they can provide whatever implementations that they want. Now, if your library has reasonable defaults, then you could export those concrete types as well, but make sure that you're accepting interfaces whenever possible. And that's what this third point is talking about. Design your functions and methods to receive interfaces whenever possible. Now, that's not always possible. If you need access to the underlying data fields, then certainly take in the concrete types. But if you're accepting behavior providers, then go ahead and try and accept those as interface types instead of the concrete types. Okay, so that covers what I want to talk about with interfaces today. Let's go into a summary and review what we've talked about. In this video, we've talked about interfaces and how to use them in the Go language. We started with a discussion of the basics of interfaces, so how to create them and how to implement them. And we ended up with code that looks something like this. So we're defining an interface as a type. So we're going to start with the type keyword, the name of the interface, and then the keyword interface. And then inside of curly braces, things are going to be a little bit different than if we were defining a struct, for example. If we were defining a struct, we would put data fields inside of the curly braces because we're defining the data that that structure is holding. With interfaces, we're defining behaviors, however. So instead of adding data fields, we're going to add method signatures. So we see here in this example, we're going to define a write method that accepts a slice of bytes and returns an integer and an error. And then we implement that interface by creating a method on our type that has the same signature. So we don't have to explicitly state that we're implementing the interface. We implement the interface by implementing the interface, by having the methods there that match the type signature for the interface's methods. Then we talked about how to compose interfaces together, and how this is a preferable approach versus creating a single monolithic interface. If you can, break that interface down into smaller types and then compose them together. And we did that something like this. So we're going to create multiple interfaces. So we have a writer interface and a closer interface. And then when we compose them together, just like when we compose structs by embedding, we can embed interfaces into one another. So we can create a writer-closer interface that embeds the writer interface and the closer interface. So to implement that writer-closer interface, you have to implement the write method because that's defined by the writer interface, and you have to implement the close method as it's defined by the closer interface. So by doing this, you can actually pass smaller chunks of your interface around your application. So for example, if a method only needs a writer, it doesn't need a closer, then you can actually pass this writer-closer as a writer, and it'll work just fine, versus passing the entire writer-closer along and potentially exposing methods to the consumer that aren't really necessary. Then we talked about type conversion and how we can drill through the interface to get at the underlying types in case we need to work with those directly. So we had an example here where we created a writer-closer instance and the underlying type was a pointer to a buffered writer-closer, and how we could cast that back to a pointer to a buffered writer-closer by using this syntax here where we have a dot after the object, and then inside of parens we put the type that we want to cast to. Now, we learned that when we did this, if the type assertion failed, then we're actually going to panic our application. So remember to use that "OK" syntax if you want to get a Boolean variable out that you can run tests against to see if that type conversion succeeded. And then we talked about the empty interface and type switches. The empty interface is nothing magic. It's just an interface defined on the fly that has no methods on it. Now, it's special in that every type in Go implements the empty interface. So you can store anything you want in a variable of type empty interface. And then very often we're going to pair that with what's called a type switch. And we see an example of that here, where we're going to use the switch keyword, we're going to have the object, and then dot and parens like we do with the type assertion. But instead of having a concrete type that we're asserting against, we put the keyword type in there. And then in our case statements, we're actually going to put in the data type that we're asserting against. So in this case, we're looking for integers or strings, or we have a default case in case the value stored in I is neither an integer nor a string. After that, we talked about implementing with values versus pointers. And we learned about a concept called method sets. Now, when you're working with types directly, you never have to think about this because the methods are always all of the methods assigned to that type. But with interfaces, the rules change a little bit. The method set of a value is all of the methods with value receivers. So if you're going to try and implement an interface with a value type, then all of the methods that implement that interface have to have value receivers. With pointers, things are a little bit more flexible. Because pointers always have access to the underlying type as well, the method sets for a pointer is all of the methods regardless of the receiver type. So all of the value receivers as well as all of the pointer receivers. So pointer types are definitely more flexible when you're implementing interfaces. Just keep in mind, you don't want to assign pointer receivers everywhere without thinking about the idea that that gives access to the underlying data of that type, and so that can allow methods to alter that underlying data even if you don't want them to. So be careful when you make that choice about using pointer receivers or value receivers. The last thing that we talked about were some best practices that have evolved over the last few years about using interfaces in the Go language. And we talked about use many smaller interfaces whenever possible, and then if you need larger interfaces, go ahead and compose those together with interface composition. Don't export interfaces for types that will be consumed. So if you're creating a library and somebody else is going to be consuming a type, go ahead and publish that concrete type out there. Don't create an interface assuming you know how people are going to use it. Allow them to create the interfaces that your type will implement. That way they don't have to implement a whole bunch of methods in their test suite that they never even use. Do export interfaces for types that you will be consuming, however. So again, these 2 points are exactly opposite of how you're going to think about interfaces if you're coming from another language such as C# or Java that have explicit implementation of interfaces. So when you're defining a type that you're going to be consuming in your package, then go ahead and export interfaces. That way whoever's using your package can create their own concrete types and implement the interfaces that you need, so you don't need to worry about the implementation. You just need to worry about the behaviors that they're exposing to you. And then, if possible, define your functions and methods to receive interfaces. Don't get too crazy with this, so don't go over the top. Use common sense with this. But if you have the option of receiving interfaces, for example, if you don't need access to the underlying data, then go ahead and define an interface that you're going to be receiving. That way, it makes your methods and functions more flexible, since you can have multiple implementations that you never thought about at design time, and your functions and methods will continue to work even when those new concepts are thrown at your application. I want to have a conversation about the tools that we have available to implement concurrent and parallel programming in the Go language. Now, if you've come this far in the series, or if you've done any research in Go at all, concurrent programming is one of the hottest topics that is talked about, especially among people who are learning the Go language for the first time. So we're going to talk about this concept of a Go routine and how that enables us to create efficient and highly concurrent applications. We'll start our conversation by learning how to create Go routines themselves. So this is going to be the basics of how we create Go routines and how we can work with them a little bit. Then we'll move into a conversation about synchronization, and we'll talk about two concepts, wait groups and mutexes, and how we can use those to get multiple Go routines to work together. Because one of the challenges that we're going to have with Go routines is also one of the greatest advantages. Go routines are going to allow our application to work on multiple things at the same time. However, you're often going to run into situations where you need a certain bit of functionality in your application to wait until one or more of those concurrent calculations is complete. So we'll talk about how to use synchronization primitives in order to do that. Then we'll move into a discussion of parallelism. Now, up to this point, our conversation is going to be about concurrency in the Go language. And concurrency is just the ability of the application to work on multiple things at the same time. It doesn't mean it can work on them at the same time, it just means it has multiple things that it can be doing. When we talk about parallelism, we'll talk about how we can take our Go applications and enable them to work on those concurrent calculations in parallel, or in other words, introduce parallelism into our applications. And finally, we're going to wrap this video up again with a little section on best practices, just to talk about some of the gotchas that you can run into with concurrent and parallel programming, and some of the tools that are available to help keep your application safe and away from those minefields. Okay, so let's get started by talking about how to create Go routines. Okay, so the first thing that you're going to notice is that we're in Visual Studio Code right now. Now the reason for that is, while we can certainly play with Go routines in the playground, when we start to get into parallelism, that's going to be limited by the playground because the playground only enables us to use one core at a time. So when we're running locally, we can use as many cores as we want, so we can truly run our applications in parallel. So some of the things that I want to show you are going to be easier to illustrate in this environment. So the first thing that I want to show you is how we can create our very first Go routine. So the first thing that we're going to need to do is we're going to need to have a function here. So I will create a function called sayHello. And this is going to be a very simple function. All it's going to do is, well, say hello. So we'll start with that, and that's going to be just enough for us to get started seeing what's going to happen with our application. So we can, of course, call the sayHello function and call that from the main function, so we can run this application by just using go run and pointing it to that file, and of course it says hello, so no big surprises there. Now, to turn this into a Go routine, all we have to do is in front of the function invocation, just type the keyword Go. Now what that's going to do is that's going to tell Go to spin off what's called a green thread and run this sayHello function in that green thread. Now I need to take a little bit of a moment here to talk about threads. Most programming languages that you've probably heard of and worked with use OS threads or use operating system threads. And what that means is that they've got an individual function call stack dedicated to the execution of whatever code is handed to that thread. Now, traditionally, these tend to be very, very large. They have, for example, about 1 megabyte of RAM. They take quite a bit of time for the application to set up. And so you want to be very conservative about how you use your threads. And that's where you get into concepts of thread pooling and things like that, because the creation and destruction of threads is very expensive. And so we want to avoid that in most programming languages, such as Java or C#. Now, in Go, it follows a little bit of a different model. And as a matter of fact, the first place I saw this model was used by the Erlang language. And this is using what's called green threads. So instead of creating these very massive, heavy overhead threads, we're going to create an abstraction of a thread that we're going to call a Go routine. Now, inside of the Go runtime, we've got a scheduler that's going to map these Go routines onto these operating system threads for periods of time. And the scheduler will then take turns with every CPU thread that's available and assign the different Go routines a certain amount of processing time on those threads. But we don't have to interact with those low-level threads directly. We're interacting with these high-level Go routines. Now, the advantage of that is, since we have this abstraction, Go routines can start with very, very small stack spaces because they can be reallocated very, very quickly, and so they're very cheap to create and to destroy. So it's not uncommon in a Go application to see thousands or tens of thousands of Go routines running at the same time, and the application has no problem with it at all. Now, if you compare that to other languages that rely on operating system threads that have 1 megabyte of overhead, there's no way you're going to run 10,000 threads in an environment like that. So by using Go routines, we get this nice, lightweight abstraction over a thread, and we no longer have to be afraid of creating and destroying them. So anyway, let's go ahead and run this and see what happens, and it's going to be a little disappointing because you notice that our message doesn't print out. And the reason for that is our main function is actually executing in a Go routine itself. So what we did here in line 6 was we told the main function to spawn another Go routine, but the application exits as soon as the main function is done. So as soon as it spawned that Go routine, it finished. It didn't have any more work to do. So the sayHello function never actually had any time available to it to print out its message. So we can get around that a little bit by using a horrible practice, but it's good enough to get us started in understanding this. So we'll just put an arbitrary sleep call in here in order to get the main function to delay a little bit. Now when we run the application, we see that we do get our hello message printed out. Now, as opposed to our first run of this, it's not actually the main function that's executing this code. It's a Go routine that we're spawning off from the main function, and that's what's responsible for printing out the message. Okay, now this is a pretty typical use case of a Go routine, where we're using the Go routine to invoke a function. But we don't have to do that. As a matter of fact, let me just drop in this example here, which is basically the same, except for instead of using a named function, I'm using this anonymous function here. So notice that I've got this anonymously declared function, and I'm invoking it immediately, and I'm launching it with the Go routine. Now what's interesting about it is I'm printing out the message variable that I've defined up here on line 9 down here inside of the Go routine. So if I run this, we do in fact see that it works. Now the reason that it works is Go has the concept of closures, which means that this anonymous function actually does have access to the variables in the outer scope. So it can take advantage of this MSG variable that we declared up here on line 9 and use it inside of the Go routine, even though the Go routine is running with a completely different execution stack. The Go runtime understands where to get that MSG variable, and it takes care of it for us. Now the problem with this is that we've actually created a dependency between the variable in the main function and the variable in the Go routine. So to illustrate how that could be a problem, let me modify the example just a little bit. So I'm declaring the variable message and setting it equal to hello. I'm then printing it out in the Go routine, and then right after I launch the Go routine, right here on line 13, I'm reassigning the variable to goodbye. So if I go ahead and run this, you see that we in fact get goodbye printed out in the Go routine, not hello, like you might expect based on how the program is written. And the reason for that, and it's not always going to be guaranteed to execute this way, but most of the time, the Go scheduler is not going to interrupt the main thread until it hits this sleep call on line 14. Which means, even though it launches another Go routine on line 10, it doesn't actually give it any love yet. It's still executing the main function. And so it actually gets to line 13 and reassigns the value of the message variable before the Go routine has a chance to print it out. And this is actually creating what's called a race condition, and we'll come back and talk about race conditions at the end of this video, but this is a bad thing, and generally it's something that you want to avoid. So while you can access variables via the closure, it's generally not a good idea to do that. So if that's not a good idea, what are your other options? Well, notice that we have a function here, and this is just a function invocation. There's nothing special about it just because we put the Go keyword in front of it. It's just a function. So functions can take arguments. So what happens if we add a message argument here, and then down in the parens where we're actually invoking the function, what if we pass in the message parameter? Well, since we're passing this in by value, so we're actually going to copy the string hello into the function, then we've actually decoupled the message variable in the main function from the Go routine. Because now this message that's going to print out is actually a copy that we're passing in when we're invoking the function for the Go routine. So now if we run this, we see that we get hello printed out. So this is generally the way that you're going to want to pass data into your Go routines. Use arguments to do that and really intend for the variables to be coupled together. Now this example so far is working, but it's really not best practice. And the reason it's not best practice is because we're using this sleep call, so we're actually binding the application's performance and the application's clock cycle to the real world clock. And that's very unreliable. So in order to get your applications to work, you're typically going to have to sleep for a very long time relative to the average performance time in order to get the performance to be reliable. So we don't want to use sleep calls in production, at least not for something like this. So what are the other alternatives? Well, one of the other alternatives that we have is to use what's called a wait group. So let's go ahead and add one in, and then while we're doing that, we'll talk about what they are. So I'm going to create another variable, and it looks like my auto formatting just helped me here. And we'll pull that from the sync package, and we'll create an object of type wait group. So I just need to put my curly braces here to initialize it. Now what a wait group does is it's designed to synchronize multiple Go routines together. So in this application, we've got two Go routines that we care about. We've got the Go routine that's executing the main function, and we've got this Go routine that we're spawning off here on line 13. So what we want to do is we want to synchronize the main function to this anonymous Go routine. So we're going to do that by telling the wait group that we've got another Go routine that we want it to synchronize to. It starts off synchronizing to 0, and so we're going to add 1 because we want to tell it that we're going to synchronize to this Go routine right here. Now once it's done, we don't need this line anymore. Once it's done, we're going to go ahead and exit the application, and we will do that by just waiting on the wait group, and we do that by using the wait method right here. Now, when the Go routine is done, then it can tell the wait group that it's actually completed its execution. And we do that by using the done method. So if we execute that, basically what that's going to do is it's going to decrement the number of groups that the wait group is waiting on. And since we added 1 and it's going to decrement by 1, it'll be down to 0. And then the wait method will say, oh, okay, it's time for us to go ahead and finish up our application run. So if I save this off and I go ahead and run it, we see in fact that our application is performing as it did before, but now it's taking just enough time to complete the execution. We're not relying on the real world clock anymore and having to jimmy around with variables and hope that everything stays consistent. Now in this example, we're just synchronizing two Go routines together, but only one of the Go routines is really doing any work. The main function in this example is just storing data and spawning other Go routines. But we can have multiple Go routines that are working on the same data, and we might need to synchronize those together. And that can be a little bit tricky. So let me drop in this example here and we'll talk about it. So I'm creating a wait group again up here on line 8, and then I'm initializing a counter variable. Inside of my main function, I'm actually spawning 20 Go routines, because inside of this for loop, each time I run through, I add 2 to the wait group to let it know there are 2 more Go routines that are running. And then I spawn a say hello, and then I spawn an increment here. And then I just have a wait method call here on line 17, just to make sure that the main function doesn't exit out too early. Now in say hello, all I'm going to do is I'm going to print out hello, and then I'm going to print out the counter value. And then in the increment function down here, I'm just going to increment the counter by 1. Now after each one of those is done, I'm going to call the done method on the wait group, and everything should be just fine. Now notice that I've broken my own rule here. The wait group is actually being accessed globally in this application, and that makes sense because I actually do want to share this object, and the wait group is safe to be used concurrently like this. It's designed to be used in this way. So let's go ahead and run this application and see what's going to happen. So our intuition says that we're going to print say hello, so it should print say hello 0 because the counter's value is 0 right here, and then it's going to increment it, and then it's going to say hello again, it's going to increment it, so it should say hello number 0, hello number 1, hello number 2, and so on. So let's go ahead and run this and see what happens. And we see that we get a mess. We in fact don't have any kind of reliable behavior going on here. We printed 1 twice and then 2, 3, 4, 5, so that seemed to work consistently. And then we jumped all the way to 9. We printed 10 out twice, and then we went back to 9 for some reason. And if we run this again, we'll get a completely different result. So what's happening here is our Go routines are actually racing against each other. So we have no synchronization between the Go routines. They're just going hell-bent for leather and going as fast as they can to accomplish the work that we've asked them to do, regardless of what else is going on in the application. So in order to correct this, we need to find a way to synchronize these guys together. Now we could probably find a way to use a wait group on this, but we've already talked about wait groups, so I want to talk about another way to do this. So we're going to introduce this concept of a mutex. So with a mutex, let me paste this example in here, and then we'll talk about what it does. But a mutex is basically a lock that the application is going to honor. Now in this case, you see on line 11, I'm creating what's called an RW mutex, which is a read-write mutex. Now a simple mutex is simply locked or unlocked. So if the mutex is locked and something tries to manipulate that value, it has to wait until the mutex is unlocked and it can obtain the mutex lock itself. So what we can do with that is we can actually protect parts of our code so that only one entity can be manipulating that code at a time. And typically what we're going to use that for is to protect data to ensure that only one thing can access the data at a single time. With an RW mutex, we've changed things a little bit. We've basically said as many things as want to can read this data, but only one can write it at a time. And if anything is reading, then we can't write to it at all. So we can have an infinite number of readers, but only one writer. And so when something comes in and makes a write request, it's going to wait till all the readers are done, and then the writer is going to lock the mutex so nothing can read it or write it until the writer is done. So in this modification, actually I don't want to talk about that line yet. We'll come back and revisit that. So in this modification, what I've done here is I'm attempting to use a mutex to synchronize things together. So the modification is down here. In my say hello, I'm just reading the value of the counter variable, and that's what I'm trying to protect. I'm trying to protect the counter variable from concurrent reading and writing, because that's what was getting us into trouble. So in line 22, I obtain a read lock on the mutex, and then I print out my message, and then I release that lock using the runlock method. Now in the increment, that's where I'm actually mutating the data, so I need a write lock, and so I'm going to call the lock method on the mutex, increment the value, and then I'm going to call unlock. Now if I run this application, I actually haven't gotten quite where I want to be. So I don't get the weird random behavior that I was seeing before, but you notice that something seems to be out of sync still, because I get hello 1, hello 2, and then it stays at 2. And if I keep running this, I actually can get different behaviors, but notice that I'm always going in the proper order. So I fixed part of my problem, but I haven't fixed all of it yet. So I can keep running. Actually, that one got pretty close, but there's obviously something else going on here. Well, the reason that we have an issue here is we're still working within the Go routines. So if this say hello function gets executed twice by its Go routines, and the increment function doesn't get called in between, that's where we get this behavior here, where we actually get the same message printing out twice, because we don't have a chance to lock this mutex before we try and read it that second time. So the way to address this is we actually have to lock the mutex outside of the context of the Go routine so we have a reliable execution model. So let's go ahead and paste in a small modification here. Now all I've done is I've moved the locks out here. So the locks are now executing before each Go routine executes, and then I unlock them when the Go routine is done. So if I run this, we actually see that I now get the behavior that I expect. I see 0 through 9 printed out, and if I run it again, and I run it again, and I run it again, everything is working great. So the reason that this is working is I'm actually locking the mutexes in a single context. So the main function is actually executing the locks, and then asynchronously I'll unlock them once I'm done with the asynchronous operation. Now the problem with this application is I basically have completely destroyed concurrency and parallelism in this application, because all of these mutexes are forcing the data to be synchronized and run in a single threaded way. So any potential benefits that I would get from the Go routines are actually gone. As a matter of fact, this application probably performs worse than one without Go routines, because I'm mucking around with this mutex and I'm constantly locking it and unlocking it. So this is an example where if this is all that this application needed to do, we would actually be much better served by removing the Go routines and just running this with a single execution path and removing any concurrency at all. However, there are often situations where you can get a significant advantage by running things in parallel, and so you can use wait groups or mutexes in order to synchronize things together and make sure that your data is protected and everything is playing well together. Now I have this line in here, and I apologize for that. I really shouldn't have had that in these earlier examples, but I do want to talk about this function from the runtime package called GoMaxProx. So in modern versions of Go, if you look at this GoMaxProx variable, let's just go ahead and execute this simple program. All it's going to do is it's going to tell me the number of threads that are available. So it prints out that there are 4 threads available in the application. And as a matter of fact, let me just add this carriage return in here and run this again. That way things look a little better. And you see that I have 4 threads available. So by default, what Go is going to do is it's going to give you the number of operating system threads equal to the number of cores that are available on the machine. So in this virtual machine, I've exposed 4 cores to the VM, so I have by default 4 OS threads that I can work with. Now, I can change that value to anything I want. So for example, I can change that to 1, and now my application is running single-threaded. So now I have a truly concurrent application with no parallelism at all. So this can be useful in situations where there's a lot of data synchronization going on, and you really need to be careful to avoid any kind of race conditions that parallelism can incur, and maybe there's no better way to do it. Now, I would say there's an architecture problem there, but it is possible to run an application in a single-threaded way by setting GoMaxProx equal to 1. Now, if you're wondering what this -1 does, when you invoke the GoMaxProx function, it actually returns the number of threads that were previously set, and if you pass a negative number, then it doesn't change the values. So this GoMaxProx -1, all that's doing is that's letting us interrogate how many threads we have available. Now, we can also set this to, for example, 100. There's nothing stopping us from creating a massive number of operating system threads. Now, what I've found in working with Go is that GoMaxProx is a tuning variable for you to work with. So the general advice is 1 operating system thread per core is a minimum. But a lot of times you'll actually find that your application will get faster by increasing GoMaxProx beyond that value. Now, if you get up too high, like for example 100, then you can run into other problems because now you've got additional memory overhead because you're maintaining 100 operating system threads. Your scheduler has to work harder because it's got all these different threads to manage. And so eventually the performance peaks and it starts to fall back off because your application is constantly rescheduling Go routines on different threads. And so you're losing time every time that occurs. So as you get your application closer to production, I would encourage you, definitely develop with GoMaxProx greater than 1 because you want to reveal those race conditions as early as possible. But just before you release to production, you might want to run your application through a performance test suite with varying values of GoMaxProx to see where it's going to perform the best. Now, the last thing that I want to talk about are some best practices to keep in mind when you're working with Go routines in the Go language. So let's take a look at those next. Go routines in the Go language are very powerful, and it can be easy to let them get a little bit out of hand. So I want to go through and give you some advice on how to work with Go routines in your own applications. The first bit of advice is if you're working in a library, be very, very careful about creating Go routines yourself. Because generally it's better to let the consumer control the concurrency of the library, not the library itself. If you force your library to work concurrently, then that can actually cause your consumers to have more problems synchronizing data together. So in general, keep things simple, keep things single-threaded, and let the consumer of your library decide when to use a Go routine and when not to. Now, this advice can be softened a little bit if you have a function call that's going to return a channel that'll return the result. Then having the Go routine in there might not be such a bad thing because your consumer never really has to worry about how that unit of work is getting done. They don't really care if it's running concurrently or not because they are just going to be listening for the result on a channel, but we haven't talked about channels yet. So we'll revisit that topic in the next video. But for now, if you're creating a library, try and avoid Go routines, at least Go routines that are going to be surfaced to the consumer and have them forced to work with them. When you create a Go routine, know how it's going to end. Now, we're going to see how to do this a little bit more when we talk about channels, but it's really easy to have a Go routine launched as kind of a watcher Go routine. So it's going to be just sitting out there listening for messages to come in, and it's going to process those messages as they arrive. However, if you don't have a way to stop that Go routine is going to continue on forever. And so it's constantly going to be a drain on the resources of your application. And eventually, as the Go routine ages, it could even cause other issues and cause your application to crash. The other thing that I want to give you some advice about is check for race conditions at compile time. So I want to jump back over to the editor and show you how to do that, but it's very important and very simple to do in most environments that Go runs in. So let's jump over to the editor and take a look at that. And in order to see it, we don't have to go any further than this example. Now I know this is right from the beginning of the video and it's got sleeps in there and it's got some bad practices, but if you remember, if we run this application, then it prints goodbye instead of the hello message that we originally printed. So how could we have detected this without running the application? Well, you might not think it's terribly important to be able to do that because it's obvious we've got some kind of a problem here and all we have to do is apply our debugging skills. But there are other cases where this is very, very subtle and very, very hard to track down without a little bit of help. Well, fortunately, the Go compiler has quite a bit of help available to you, and it's as simple to invoke as just adding a -race flag to go run, go install, go build, whatever you're using to get your application up and running. So let's go ahead and try that and see what it says about our little application here. And you notice it does run the application because we invoked go run, so we see goodbye printed here. But notice what we got up here. We got this data race message. So it's telling us it sees that the same area of data is being accessed by two different executing Go routines. So it says the first one that it found was in Go routine 6, which is an internal identifier. Unless we're profiling, we've got no idea what Go routine 6 is. But it does tell us it was invoked on line 11. So apparently in this run, Go routine 6 was this Go routine right here, and it was accessing the MSG variable. It also sees that we accessed the MSG variable on line 13, which is in our main function. And so by adding the dash race flag, we get all of this additional information where the Go compiler itself analyzes our application and tries to determine if we have any race conditions. So I would strongly encourage you, if you've got any kind of concurrency at all in your application, you're going to want to run this because it's very simple check, it runs very, very quickly, and it's going to help you prevent very subtle bugs from getting into your production code. Okay, so that's what I have to talk about with Go routines. Maybe you were expecting more, but Go routines are really quite simple. Now, when we get into our next conversation, which will be about channels, things get a little bit more complicated, but Go routines are relatively straightforward. So let's go into a summary and review what we've talked about in this video. In this video, we learned about Go routines and how we can use them to create concurrent and parallel execution paths in our applications. We started by learning how to create Go routines themselves. And we learned that by adding the Go keyword in front of a function call, we've created a Go routine, and that's all that it takes. There's no special semantics, there's no special things that need to be done. It's simply a function call with the keyword Go in front of it. Now, when we're using anonymous functions, we in general want to pass data as local variables. So you want to add a parameter into that anonymous function and pass data into the Go routine instead of relying on the closures to prevent any kind of race conditions as you try and manipulate that data. Now, that's not always true. We saw with wait groups that we access that globally because that was our intention. We truly did want that to be available in multiple scopes. But even then, we could pass a pointer in order to be very clear about what information that Go routine should have access to. Then we talked about the different ways that we can synchronize multiple Go routines together. One of the challenges that we have with Go routines is now we've got all sorts of things happening, and there's no way to ensure without synchronization how they're going to interact with one another. Now, for a lot of concurrent calculations, that's not a problem at all because the two might not be related to one another. But often you get into situations where you're relying on the result of multiple calculations, or something needs to know the result of the work that's been done, or you've got a shared memory issue and you need to make sure that those Go routines aren't trying to manipulate the same data at the same time. So we can use wait groups to wait for groups of Go routines to complete. So we saw that we have three methods that are interesting there. We have the add method to inform the wait group that there are more Go routines for it to wait on. We have the wait method that's going to block the Go routine that it's called on until the wait group is completed. And then we have the done method available on that wait group that lets the wait group know that one of the Go routines is completed with its work. We also talked about the mutex and the RW mutex and how those are generally used to protect data. So if you have a piece of data that's going to be accessed in multiple locations in your application, then you can protect that access by using a mutex or an RW mutex to ensure that only one Go routine is manipulating that data at one time. We then talked about parallelism and how parallelism can introduce some really tricky challenges into your Go applications. We talked about how by default Go will use the number of CPU threads equal to the number of available cores on the computer that it's running on. We talked about how we can change that by using the Go max procs function from the runtime package. And we talked about how more threads will generally increase performance, but too many can actually slow it down. So in general, if you're developing an application, you want to start from day one with Go max procs greater than 1 to find any concurrency and any race conditions early on in your application development. But don't settle on a final number until right as you get close to production and you have a performance test suite that you can work with to find out what the best value for Go max procs is for your application. Because while the starting number is a very good number to start with, a lot of applications actually perform better with a value higher or lower than that default value. And finally, we wrapped up with a discussion of some best practices to keep in mind when you're working with Go routines. We learned that if you're a library developer, You should avoid the creation of Go routines that are going to be exposed to the consumer of your library. Let the consumer control the concurrency of your application because they're the ones that are in the best place to know if something needs to be executed single-threaded or if it can be executed concurrently. When creating a Go routine, know how it's going to end. It's very easy to get into situations where Go routines start leaking memory because they're never cleaned up, because they never quite get done with their work. Now, normally a Go routine is killed as soon as it finishes its execution. And we saw that with the main function. The main function runs in a Go routine, and that Go routine terminates as soon as the main function exits. We also saw in our say hello function, as soon as it printed its message out and the function exited, that Go routine was killed and it was cleaned up. So it was very clear when those Go routines' life cycle was going to be over. However, if you've got Go routines that are listening for messages in a continuous loop, then make sure that you code in a way to shut those Go routines down so that once you're done using them and clean up the memory that they're using. Also, as you're going along with your application development, check for race conditions. It's not that hard to do. You just have to add -race onto the Go command that's compiling your application, and then the Go compiler is going to analyze your application and try and locate places in it that have the potential of accessing the same memory at the same time or in an unsynchronized way, causing very subtle and potentially very disastrous bugs for your application when it gets to production. Over the course of this video series, we've talked about a lot of structures and techniques and tools that are available in order to get started successfully programming with the Go language. Well, I want to wrap up that discussion in this video by talking about one of the features that makes Go really stand out when you're looking for different languages to work with, and that is this concept of channels. Now, most programming languages that are out there were originally designed with a single processing core in mind. And so when concurrency and parallelism came into play, they were really kind of bolted onto the side. And so a lot of times you're actually going to be working with third-party libraries and packages in order to help with data synchronization and things like that. Well, Go was born in a multiprocessor world. So every computer that was out there when Go was invented had more than one processing core. So it made sense, as the language was being designed, to consider concurrency and parallelism from the beginning. Now, in the last video, we talked about Go routines and how Go abstracts the concept of a thread into this higher concept called a Go routine to allow hundreds or thousands or even tens of thousands of things to be going on in your application at the same time. Well, in this video, we're going to be talking about channels and how those can be used to pass data between different Go routines in a way that is safe and prevents issues such as race conditions and memory sharing problems that can cause issues in your application that are very difficult to debug. So we're going to start this talk by talking about the basics of channels. So we'll talk about how to create them, how we can use them, how we can pass data through them. Then we'll talk about how we can restrict data flow. Now, a basic channel is a two-way street. We can send data in and we can get data out. But that's not always what you want to be able to do with a channel. Sometimes you want a send-only channel or a receive-only channel, and we'll talk about how to do that in this second section. Then we'll talk about buffered channels and how we can actually design channels to have an internal data store so that they can store several messages at once, just in case the sender and the receiver aren't processing data at the same rate. Then we'll talk about how we can close channels once we're done with them. We'll then revisit the topic of for-range loops, and we'll learn how we can use channels with a for-range loop. And then we'll wrap up our discussion by talking about select statements, which is kind of like a switch statement, but specifically designed to work in the context of a channel. Okay, so let's go ahead and dive in and learn the basics of working with channels. So when we're working with channels in the Go language, we're almost always going to be working with them in the context of Go routines. And the reason is because channels are really designed to synchronize data transmission between multiple Go routines. So let's go ahead and get started by creating some Go routines. Well, actually, the first thing that I need to do is I need to create a wait group, because as you'll remember from the last video, we use wait groups in order to synchronize Go routines together. So we're going to use the wait group to synchronize the Go routines to make sure that our main routine waits for all of our other Go routines to finish. And then we're going to use channels in order to synchronize the data flow between them. So we got two different synchronization mechanisms going on in this little application. The next thing we need to do is we need to create a channel. Now, channels are created with the built-in make function, and there really is no shortcut around this. Now, a lot of uses of the make function, you can actually use other forms. When you're creating a channel, there's enough internal mechanisms that need to fire that you have to use the make function in order to allow the runtime to properly set up the channel for you. Now, in the simplest form of the make function when working with channels, we're going to use the chan keyword to say that we want to create a channel, and then we're going to provide the data type that's going to flow through the channel. Now, you can pick any data type that you want. We're just going to be using integers here. But keep in mind that this means that the channel is strongly typed. You can only send integers through this channel that we're creating here. Similarly, if we provided strings, we can only pass in strings. If you provided pointers to integers, you can only send in pointers to integer. You get the general idea. So when you create a channel, you're going to create that channel to accept messages of a certain type, and it's only ever going to receive and send messages of that type. Now in this initial example, we're going to have two Go routines I'm going to spawn. So I'm going to add 2 items to my wait group, and then we'll go ahead and create those Go routines, and then we'll talk about those. So let me just drop in the rest of the code here. And you can see my first Go routine is an anonymous function. Actually, both of them are. And this first one is going to be receiving data from the channel. So this Go routine is actually going to be my receiving Go routine. And then this channel is actually going to be my sending Go routine. So the way that we send a message into a channel is as you see here. We're going to use this arrow syntax, so we're going to use a less than and a dash. And when we're putting data into the channel, we list the channel first, then we have this arrow, and then the data that we want to pass in. So imagine that the arrow is pointing in the direction that we want the data to flow. So we want the data to flow into the channel, and so the arrow is pointing toward the channel. Similarly, if we want to receive data from the channel, then we're going to put the arrow on the other side. So we're going to use that same less than and dash, but it's going to be before the channel, and so we're going to be pulling data from the channel. So in this line right here on line 14, we're going to be receiving data from the channel and assigning it to the variable I. And then after we're done, we're going to call the done method on our wait groups, and we're just going to print the value out. So all we're doing here is this Go routine is going to be sending the value 42. This Go routine is going to be receiving whatever value comes out of the channel, which in this case, of course, will be 42, and it's going to print that out to the console. So let's go ahead and run that, and we see that, in fact, it does work. So the nice thing about doing this is since we're sending a copy of the data through the channel, we could manipulate the variable assigned here. So, for example, we could actually start this off with I set equal to 42, and we can pass in I. And then afterwards, we could reassign I, and it doesn't matter, because like with all other variable operations in Go, when we're passing data into the channel, we're actually going to pass a copy of the data. So when we manipulate it afterwards, the receiving Go routine doesn't really care that we change the value of the variable. It's not affected by that at all. Now, another common use case for Go routines is if you have data that's asynchronously processed. So maybe you can generate the data very, very quickly, but it takes time to process it. Or maybe it takes a long time to generate that data, so you've got multiple generators, but it can be processed very quickly. So you might want to have a different number of Go routines that are sending data into a channel than you have receiving. So let's take a look at how we can do that. So it's a slight modification to the example that we just went through. Instead of just having the Go routines fire once, I'm actually creating Go routines inside of this loop here. So I'm going to create 5 sets of Go routines. So each one of the groups is going to have a sender like we have here, which is exactly what we had before, and then we're going to have a receiver, which is, again, just like we had before. So by the time the application's done, we're going to spawn 10 Go routines here, 5 senders and 5 receivers, and all of them are going to be using this single channel to communicate their messages across. So if we go ahead and run this, we see that we do get 5 messages received. Okay, so this works out really well, but I will warn you, if you start playing around with this and you decide to start moving the senders and receivers to make them asymmetrical, things won't work very well. So one of the things you might want to do to play with this example is take this Go routine and move it outside of the for loop. So you're going to have one receiver and multiple senders at the end of this. Well, that actually isn't going to work right now, because if you think about how this Go routine is going to process, it's going to receive the message coming in from the channel, it's going to print, and then it's going to exit. But then down here in the loop, we're actually going to spawn 5 messages into that channel. So we can only receive 1, but we're sending 5. And if we run this, we're actually going to run into a problem, and that is we see all routines are asleep, that we have a deadlock condition. And the reason for that is because we have these Go routines down here that are trying to push messages into the channel, but there's nothing that can process them. Now, an important thing to keep in mind here is the reason that this is a deadlock. And the reason for that is this line of code here is actually going to pause the execution of this go routine right at this line until there's a space available in the channel. So by default, we're working with unbuffered channels, which means only one message can be in the channel at one time. So our first go routine in this loop gets happily spun up, it pushes a message into the channel, and then it exits, and it calls this done method on the wait group. And then that message gets processed by this go routine here, and everything's happy. However, this go routine then exits, and then our next go routine comes along and tries to push another message in. Well, it blocks right on this statement, and there's nothing in our application that's going to receive that message. And that's why we see the go runtime notice that, and it's going to kill the application because it notices that we have a problem, and it doesn't know how to resolve it. Now, I want to go back to our previous example, and actually I'm going to modify things slightly here, because I want to show you that, notice that we're just working with the raw channel. So this is perfectly valid code for us to write. As a matter of fact, if I go ahead and run this, we see that we get two messages printed out, but look at how that's happening. So this go routine is pushing a message into the channel. That message is then being received up in this go routine and printed out. This go routine then, the one that received this message, is then putting a message back into the channel. And that is then being received down here in this go routine, which is then printing the message out. So both of these go routines are acting as readers and writers. Now, that may be a situation that you want, but very often you want to actually dedicate a go routine to either reading from a channel or writing to a channel. So in order to do that, what we're going to do is we're actually going to pass in the channel with a bias on the direction that it's going to be able to work with. So the way we're going to do that is by accepting variables in our go routines. So we'll start with this first one here, and we want this to be a receive-only channel. So the way we're going to do that is we want data to flow out of the channel. So you notice we're using that similar syntax. We're going to list the type of the channel, and then we're going to have this arrow coming out of it. So data is flowing out of the channel, and so this is going to be a receive-only channel. Similarly, if we want a send-only channel, we're going to give it the variable name. We're going to say that it's a channel. Now we put the send-only operator right here, and then we put the data type. So this is going to be sending data into the channel only, and this is going to be receiving data from the channel. And then, of course, we have to pass the channel into the go routines as arguments. So when we run this, we're actually going to get an error. And the reason we get an error is because we're trying to pass data into this channel, but this is a receive-only channel, so it's invalid to send data into it. And then similarly, we have an error down here on line 21 because we're trying to receive data from a send-only channel. So if we go ahead and wipe out these lines here, this line, and run, then everything works as it did before. But now it's much more clear what the data flow is in the go routine. We know that we're going to be receiving data on one side and we're going to be sending data on the other. Now, something that's a little unusual with this is notice that we're passing in a bidirectional channel, so this is just a normal channel, and we're receiving it a little bit differently. So this kind of feels like a little bit of polymorphic behavior, and this is a special aspect of channels. The runtime understands this syntax, and so it actually is going to, I'm going to use the word cast here, it's going to cast this bidirectional channel into a unidirectional channel, but that's not something you can generally do in the Go language. That is something that is specific to channels. Now, one of the problems we ran into on a previous example is we had a situation where we tried to push 5 messages into a channel, but we only had one receiver, and we noticed that the application deadlocked. Well, we can get around that in a couple of different ways. Now, I'm going to show you one way to get around that really isn't ideal for solving that problem, but I will talk about the problem that it is solving, and that is by using buffered channels. So if I go ahead and paste in this example here, we will see an example of the problem we might run into. I've simplified it a little bit from the previous example we ran into. So we've got our initial example where we've got a receive-only go routine, we've got a send-only go routine, but in our send go routine, we're actually sending 2 messages, but since we're only receiving one, we expect that we're going to run into a problem. So let's go ahead and run this. And we see that we do in fact have a problem. We received the 42 out and printed it, but there's nothing to deal with this message here that's in the channel, and so the application blows up because this go routine can never complete because it's blocked on this line. So we need a way to get around that. Now, a simple way to get around that is by simply adding a buffer here. So if we add a second parameter to the make function up here and provide an integer, that's actually going to tell Go to create a channel that's got an internal data store that can store, in this case, 50 integers. Now what that's going to do is it's actually going to allow our application to complete, but we do have a little bit of a problem here because this message is lost. So it did eliminate the panic, and I guess in one way you could say it solved the problem, but it did create another problem in that we lost this message. Now this isn't the problem that buffered channels are really intended to solve, but I do want to show you that it does create that internal store so we can receive multiple messages back out. As a matter of fact, what we can do is we can just copy this line down here and reformat this, and we don't need this colon right here. And if we run this, we see that we do get both messages printed back out. Now what a buffered channel is really designed to do is if the sender or the receiver operate at a different frequency than the other side. So you can imagine if we had a data acquisition system and maybe we retrieve data from our sensors in a burst transmission. So maybe we're acquiring data from seismometers and we're monitoring earthquakes. Well, maybe those seismometers, in order to conserve power, don't send their data continuously. They're going to send a burst transmission maybe once an hour. So every hour we're going to get a burst transmission that maybe lasts 5 or 6 seconds that's going to contain the entire hour's worth of data. So in that case, our sender is going to be inundated with data when that burst happens, and it's going to have a way to deal with it. Well, the receivers might take a little while to process that data. So in that case, what we might want to do is create a buffer here of these signals that are coming in from our seismometer that's going to be able to accept that 1 hour's worth of data, and then our receivers can pull that data off as they're able to process it and keep things working smoothly so that the channel that's receiving the data from our sensors doesn't get locked up because it doesn't have a place to put the next message. So that's really what buffered Go routines are designed to work with, is when your sender or your receiver needs a little bit more time to process, and so you don't want to block the other side because you have a little bit of a delay there. Now, if this isn't the right way to handle this situation, what is the right way? Well, the way that we typically handle something that's going to happen multiple times, such as passing a message into a channel, is by using some kind of a looping construct. And that's no different with channels as it is with anything else. So let's paste in this example where instead of processing the message once and then having this first Go routine exit, I'm actually going to use a for range loop. But notice what I'm ranging over. Instead of ranging over some kind of a collection, such as an array, a slice, or a map, I'm actually ranging over the channel. Now the syntax changes just a little bit, because if this were a slice, the first index that we pull back is going to be the index in the slice. And then the second variable we pulled out, if we had, for example, a second variable here, would be the value. Well, when you're ranging over a channel, things are a little bit different. When you pull a single value, you're actually going to get the value that's coming out of the channel. And so if we run this, we see that we do in fact get 42 and 27, but we still have a deadlock condition. So what's causing that deadlock condition? Well, before we had this for range loop, we actually deadlocked this Go routine right here, and everything died. Well, in our new application, we're actually deadlocking in the for range loop. And the reason for that is because we're continuing to monitor for additional messages, but we stopped sending messages. And so now this for range loop doesn't know how to exit, and so this Go routine is now causing the deadlock condition. So we've improved the situation. We kind of moved the needle where we're no longer deadlocking in our sender, but we are still deadlocking in our receiver. So how do we handle that? Well, the way that we're going to handle that is we have to understand how the for range loop works. So if you're using a for range loop over a slice, how many times does that iterate? Well, it executes the loop once for every item in the slice. So if you've got a slice with 5 elements in it, you're going to run through the for range loop 5 times. Well, how many elements are in a channel? Well, there can be an infinite number of elements in a channel because you can constantly push a new message into it. So what is the way to signal a for range loop with a channel that there are no more messages coming? Well, the answer is we need to close the channel. So anything that has access to the channel can do this. We're going to use the built-in close function, and we're going to pass in the channel like you see here. So what we're doing on our sending side is we're passing in 2 messages. We're passing in 42 and 27, and then we're letting the channel know we're done working with you. So we're going to go ahead and close the channel. This for range loop is going to detect that, and when we run this, now everything runs well. Because we're passing in the message 42, that gets processed in the for loop. We're passing in 27, that gets processed. Then we close the channel, that gets processed by the for range loop, which notices that the channel is closed, and it's going to exit, and it's going to terminate the loop. So when we terminate the loop, then we call the done method on the wait group, and then we exit the go routine. All of our go routines exit properly, and we have no more deadlocks. Now, we do have to be a little bit careful in closing channels, because when you close a channel, you really have to mean that you're closing the channel down. So let's try closing the channel right here and then pushing another message into it. So if we run this, we actually get a bad thing happening. So in this case, the application panicked. And why did it panic? Because we tried to send a message on a closed channel. So the issue here is we close the channel right here on line 21, and then on line 22, we tried to pass another message into it. So that is a no-no. You are not allowed to pass a message into a closed channel because the channel is closed. So you might ask, well, how do I recover from this? How do I reopen the channel or undo that or whatever? And the answer is you can't. As a matter of fact, you can't even detect if a channel is closed except for by looking for the application panicking. So call that a limitation of the Go language or not, I don't know, but you do have to be very careful that when you close a channel, nothing else is going to send a message into it. So if that is a possibility, then the only option you really have is to have a deferred function and use a recover in there to recover from the panic that gets thrown. Because in this situation, you will have a panic and there is no way to avoid it. So if in your application that's a situation that's likely to happen, then again, you're going to have to use that recover function, and you can review the video where I talked about using those. Now, on the receiving side, we do have a little bit of a different story here, because this issue is on the closing side. So we cannot send a message into a closed channel, and we can't detect if a channel is closed before we try and send a message into it. However, if we go on the receiving side, then the story gets a little bit brighter. So you might ask the question, how does the for range loop know that the channel is closed? It has to have some way of detecting it. Well, it turns out that there's more than one parameter that you can pull back from the channel. So just like when we're querying maps and we're trying to get a value out of a map and we can use that OK syntax, well, that syntax works for channels as well. So if I change this example up a little bit, and this is going to do exactly the same thing as our current example here using a for range loop, but instead of using the for range loop and having Go automatically process the closed channel for us, we're going to process this manually. So let me paste in this example and show you. So notice that I'm in a for loop in this Go routine, and I don't have any conditions on it. So this is going to execute forever. Down here then, I'm receiving a message from the channel, and I'm using the OK syntax. So I'm going to get the value from the channel in I, and I'm going to get a Boolean letting me know if the channel is open or not in the OK variable. So if the channel is open, then OK is going to be true. If the channel is closed, then OK is going to be false. So in the happy path, if OK is true, then I'm going to go ahead and print out my message. Otherwise, I'm going to break out of this for loop here because the channel is closed and I'm not going to be receiving any more messages from it. So this is functionally exactly the same as the for range construct, but we're explicitly seeing this OK syntax. So which one would you use? Well, in this situation, it would make more sense to use the for range construct, but there may be situations where you're receiving data from a channel and you are not in a loop. So maybe you're spinning off a new Go routine for every time you're processing a message, and so the loop is going to contain the spinning off of the Go routines, and so you're going to need this OK syntax because it might not make sense to use the for range loop. Now, the last thing that I want to talk about in this video are what are called select statements. So let me go ahead and paste in this code here. So we talked about in the last video how there can be situations where you create Go routines that don't have an obvious way to close. And that's what I want to try and illustrate here. So if I go ahead and run this, we see that we do get these messages printed out. So I'm just doing a simple logger implementation. So what you see here is I've got some constants that are declaring my log level. I've got a struct that I've declared that's holding the timestamp for the log entry, the severity of the log level, and then whatever message I'm trying to print out. Then I'm creating a log channel. And the way this application works is the first thing the main function does is it spins up this Go routine that's going to be my logger. And what it's going to do is it's simply going to monitor that log channel for log entries that are coming from throughout my application. So the idea is I've got a central logger, and anything that could do logging in my application just needs to know about this channel, and all of my logging logic can be hidden within the processing of those log channel messages. So the logger is down here. We've got a for range loop that's listening for messages from the log channel, and all it's doing is it's printing out a formatted message that's got the timestamp, it's got the log level, and it's got the message from the log. So no big deal here, nothing terribly exciting. Then my main function goes on to exercise that a little bit. It sends two messages into the log channel, one letting it know that the application is starting, another one letting the application know it's shutting down. And then I've got a sleep call here just to make sure that the logger go routine has enough time to process that. Now you notice my timestamps are a little funny here. That's because I'm working with the playground. I promise you this code does work. If you shift it over to Visual Studio Code, you will actually get real timestamps. But for some reason, the playground doesn't give you the current time when you call the now function. And so this is just something that we're going to have to work with in this example. Now the problem I want you to consider is, when does the logger go routine close down? So obviously, the logger go routine has to terminate sometime because the program finishes execution and we get the results back from the playground. So what's happening here is, remember, an application is shut down as soon as the last statement of the main function finishes execution. So when we finish this sleep call here, the application terminates and everything is torn down and all resources are reclaimed as the Go runtime returns all of the resources that it was using back to the operating system. So what that means is that our logger go routine is being torn down forcibly. There's no graceful shutdown for this go routine. It's just being ripped out because the main function is done. Now, in some situations, like this one, that may be acceptable. But there are many situations where you want to have much more control over a go routine because, remember what I said in the go routine video, you should always have a strategy for how your go routine is going to shut down when you create your go routine. Otherwise, it can be a subtle resource leak, and eventually it could leak enough resources that it could bring your application down. So there's a couple of different things we could do here, right? We could, of course, do a defer call here. We can pass in an anonymous function, and inside of that, we could go ahead and close the log channel. So what that's going to do is when the main function exits, it's going to go ahead and close the channel, and then we are gracefully shutting down that channel. And that works just fine. There's no issues with that. We are intentionally closing down the channel. We know how our go routine is going to close, and so this is perfectly acceptable in this use case. But this isn't what I want to show you. So this is certainly something you could use in this use case, but I want to show you another way that's very commonly used in these kinds of situations. So the way that I want to show you is using what's called a select statement. So let me go ahead and paste in that code and we'll walk through that. So the application is basically the same. I've got the same constants over here. I've got the same struct. I do have this additional channel here, and notice the type signature for it. So it's strongly typed, but it's strongly typed to a struct with no fields. Now, struct with no fields in the Go language is unique in that it requires 0 memory allocations. So a lot of times you will see a channel set up like this, and the intention is it can't send any data through except for the fact that a message was sent or received. So this is what's called a signal-only channel. There's 0 memory allocations required in sending the message, but we do have the ability to just let the receiving side know that a message was sent. So this is pretty common. You might be tempted if you're new to the language, like I first did, you send a Boolean in here, but that does actually require a variable to be allocated and copied, so it is actually better to use an empty struct because it saves a couple of memory allocations. It's a little bit minor, but it is something that if you are going to use a channel as a pure message, then you might as well go with the conventions and use this approach. So our main function is exactly the same as it was before. We've got our logger, we've got our log channel sending in a couple of messages, and then we got a sleep call here. And then inside of our logger function, we've got an infinite loop now, and we're using this select block. So what this select statement does is the entire statement is going to block until a message is received on one of the channels that it's listening for. So in this case, we've got a case listening for messages from the log channel and a case listening for messages from the done channel. So if we get a message from the log channel, then we're going to print out our log entry. If we get a message from the done channel, then we're going to go ahead and break out of this for loop. So what this allows us to do is at the end of our application, we can go ahead and pass in a message into our done channel, and that is going to be an empty struct. And I'm just going to define that empty struct on the fly here. So this is a little bit confusing syntax, But this is the type signature for my struct, so I'm defining a struct with no fields, and then I'm initializing that struct using these curly braces here. So if I go ahead and run this, you see that the application runs properly, so I do process my log messages, and then I pass in this message into my done channel when I wish the logger to shut down. So this is a common situation for you to use when you're monitoring channels and you need a way to have the Go routine that's monitoring those channels be able to terminate. So very often you're going to send in, normally as a parameter, you're going to send in this done channel, and then whatever is ready to kill the Go routine will go ahead and send a message into that done channel, and it'll go ahead and kill it. Now, one more thing that I do want to talk about, and I'm not going to actually run it because it's going to break our application here, but you can have a default case here, and if you do, then this no longer becomes a blocking select statement. So what this is going to do is if there's a message ready on one of the channels that are being monitored, then it's going to execute that code path. If not, it will execute the default block. So this is useful if you want to have a non-blocking select statement, then you need to have that default case in there. If you don't have the default case, then the select statement will block forever until a message does come in. Okay, so that's what I have to talk about with channels. Let's go into a summary and review what we've talked about. In this video, we talked about channels and how we can use them to synchronize data transmission between Go routines. We started out by talking about the basics of working with channels. And we learned that we can make our channels using the built-in make function and how that's really the only way that we have available in the Go routine to make a channel. When we do make those channels are strongly typed. So we're going to use the chan keyword to indicate that we wish to create a channel, and then we have to follow that with a data type that the channel is going to be able to send and receive. Now that data type can be anything. It can be a primitive like we see here with an integer, it can be a struct, it can be an interface, but it does have to be strongly typed. We can send a message into the channel using this arrow syntax, and the position of the arrow kind of indicates the direction that the data is going to flow. So in this case, we list the channel, we have the arrow, and then the value that we wish to send into the channel. So notice that the arrow is pointing into the channel. But when we want to receive messages from the channel, then the arrow is leading out of the channel. And so we're going to use the same arrow syntax, but the channel is going to be added after the arrow instead of before. And we can have multiple senders and receivers. As a matter of fact, it's very common for one channel to be distributed among multiple Go routines, and that way you can have multiple data generators that are sending messages into the channel, as well as multiple data receivers, and that allows you to balance the performance between senders and receivers. So if you can generate data 10 times as fast as you can process it, then you can create 10 times as many receivers, and that way you can balance the workload out between senders and receivers. We then talked about how to restrict data flow. By default, channels are bidirectional constructs, so you can send and receive data into a channel. Now, very often what we want, though, is our Go routines to be designed to handle channel data only in one direction. So we saw that we can do that by passing in the channel, but then on the receiving side, so for example in the argument list of the function, we can actually specify the direction that we can work with by, again, adding that arrow, and we either add it before or after the chan keyword, depending on what kind of channel that we want to make. We can make a send-only channel by putting the arrow after the chan keyword, and we can make a receive-only channel by adding the arrow before it. We then talked about buffered channels, and how buffered channels contain internal data stores that allow us to get around this limitation of channels. That by default, a channel will block the sender side until a receiver is available, and the receiver side will be blocked until a message is available to come out of the channel. So you can actually block a Go routine on the sending side or the receiving side of the channel. So if there's no position available in the channel to add the message, then the sending side will be blocked until a space does become available, and if there's no message in the channel, then the receiving side is going to be blocked until a message becomes available for it to work with. So in order to decouple that, we can add an integer as a second argument to the make function, and that's going to allow the channel to have an internal buffer to decouple your senders and receivers, just in case there are situations where data is generated faster than it's received. So just like it says here, we want to use buffered channels when sending and receiving have asymmetric loading. So if we can generate messages faster than we can receive them, then a lot of times a buffered channel is a really good way to go. We then moved on to talk about for range loops, and specifically how to work with them with channels. And we learned that they basically work the same way, but there are a couple of subtle differences. The first thing is, the first parameter that you're going to receive from the for range loop when working with channels is the value itself, not the index like we saw when we were using for range loops over arrays, slices, and maps. And we saw how we could use for range loops to monitor a channel and process messages as they arrive. So the for range loop is just going to keep pulling messages as they come in off the channel, and it'll process them as they come. Then when the channel gets closed, the for range loop is going to detect that, and it will go ahead and exit the loop. And finally, we talked about select statements and how they work kind of like switch statements, but they work only in the context of channels, and how they allow a Go routine to monitor several channels at the same time. Now, if they block if all channels are blocked, so if there's no messages available on any channel, then the select statement will block by default, and then when a message comes in, it will go ahead and process that on the proper case. If multiple channels receive a value simultaneously, then the behavior is actually undefined. So because of the highly parallel nature of many Go applications, you can get into situations where messages arrive on two channels at virtually the same time. So one of those cases will get the nod from the select block, but you can't be sure of which one's going to get it. So there is no rule like in switch blocks where the first one that matches is going to get it. It could be anyone. So the ordering of the cases in your select statements really doesn't matter from the standpoint of how those conflicts are going to get resolved. Now, if you do want a non-blocking select statement, remember that you can add that default case in there. So if there are no messages on any of the monitored channels, then the default case will go ahead and fire, and so the select statement will process and execution of the Go routine will continue from there. Okay, so that wraps up what I have to talk about with channels, and really it brings us to the end of the discussion that I have for this Introduction to Go series. For now, this is Mike Vansickle wishing you luck in all of your Gopher endeavors. Take care.